Hello there, and welcome to Science for Sleep, where curiosity takes the scenic route and the wonders of the universe find their way into gentle conversation. Tonight, I'd like to take you on a journey, one that begins close to home but drifts slowly, steadily into the unknown. The question is simple enough to ask, but much harder to answer. How far does the solar system actually go? We speak of planets and moons as if they form a neat family portrait. Mercury, Venus, Earth, Mars, the familiar names we learned as children, lined up like beads on a string. But the truth is far more complicated and far more fascinating. The solar system doesn't end where the textbooks often stop, at Neptune or Pluto, or even where the sun's light fades into the dimness of space. Its reach extends into places so remote that sunlight takes months, even years to arrive. Before we go too far, let me pause to ask something simple. Where are you listening from tonight? Perhaps you're on the other side of the planet. Maybe it's daylight where you are. Maybe it's night. Is the sky clear above you? Can you see any stars if you step outside? Or maybe you're tucked in, ready for rest, with curtains drawn and only the glow of a screen for company. Wherever you are, you and I are sharing this moment, and our sun, though it feels distant even at Earth's 93 million miles, is also the same star that rules every corner of the solar system we're about to explore. If you find this journey soothing, if it helps you relax after a long day, or brings you a little peace, I'd be ever so grateful if you gave the video a like and maybe subscribed. It helps this small corner of calm reach others who might be looking for a gentle voice to accompany their curiosity or just a way to ease into sleep. Now, let's begin. Because while the sun may seem like the obvious centre of the story, the truth is that the boundaries of its influence stretch far further than most people realise. The question of where the solar system ends doesn't have a single neat answer, because different definitions draw different lines in the dark. Is the solar system defined by where the planets orbit, by where the sun's gravity still has a hold, by where the stream of solar wind finally fades into the galactic breeze, or is it where the last icy fragments of ancient comets drift, untouched for billions of years? Each of these markers offers a different way of measuring distance, and none of them feel entirely complete on their own. To understand how far the solar system goes, it helps to start from what we know best, the bright interior where the planets move in steady rhythm. Here, Earth circles the Sun in a year, Mars takes 2, Jupiter more than 10. These are familiar orbits, predictable, observed for centuries. But already, if you step just beyond Neptune, the story becomes less clear. Beyond the 8 classical planets lies a region filled with icy debris, small worlds, dwarf planets, and comets in waiting. The Kuiper Belt, as it's called, stretches outward like a great ring of frozen leftovers from the solar system's birth. It contains objects far smaller than planets, but still significant in number, hundreds of thousands, perhaps millions. Pluto is simply the most famous resident. But does the solar system end at the Kuiper Belt? Not really. Because farther still, the scattered disk begins, populated with objects whose orbits take them into elongated, distant paths, some stretching thousands of times farther from the Sun than Earth. Sedna is one such object, with an orbit so vast it spends most of its time unimaginably far from anything familiar. Then, even beyond that, lies the Oort Cloud, a theoretical shell of icy fragments surrounding the solar system in every direction. The Oort Cloud is thought to be the birthplace of many long-period comets, objects that take millions of years to complete a single orbit. If it exists as scientists predict, it could extend a light year or more from the Sun, which means the solar system, in one sense, reaches almost halfway to the next star. But the Sun's influence isn't only about the icy remnants of creation. There's also the solar wind, a constant outflow of charged particles streaming from the Sun in all directions. This wind inflates a bubble around the solar system called the heliosphere, Inside the bubble, the solar wind dominates. Beyond it, interstellar space begins, where particles from the galaxy at large push back. The boundary between these two regions, known as the heliopause, is another way of defining the edge. Voyager 1, the spacecraft launched in 1977, is the first human-made object to cross it. It reported back that beyond the heliopause, the density of particles changed. The hum of interstellar space replaced the rhythm of the solar wind. That was in 2012, more than 35 years after its launch, and by then it was more than 11 billion miles from Earth. Even so, Voyager hasn't yet escaped the solar system in a gravitational sense. The sun's pull extends much farther, holding even the most distant comets in loose orbit. To fully leave the solar system in that sense would take far longer than any spacecraft we've built has yet travelled. The sun's gravity, though faint at those distances, doesn't simply stop. It stretches outward until other stars begin to pull with equal strength. This transition zone, where the sun's influence fades and the galaxy takes over, is yet another possible boundary. You can see the difficulty then. The solar system is not a neat bubble with a fixed wall. It's a layered structure, each layer defined by different physical forces. Planetary orbits, solar wind, gravity, and cometary reservoirs all offer their own versions of an edge. And depending on which definition you prefer, the solar system could be considered a few billion miles wide, or a few trillion, or even so vast it takes light itself years to cross it. As we move deeper into this topic, we'll look more closely at each of these regions, the familiar and the unfamiliar alike. We'll travel outward, step by step, from the inner planets you know well, past the gas giants and icy dwarfs, past the Kuiper Belt, the scattered disk, the heliopause, and into the ghostly realm of the Oort Cloud. Along the way, we'll ask what it really means to belong to the solar system. Is it a matter of orbit, of history, of influence? Or is it a human label for something nature doesn't bother to define so neatly? The solar system is a family, but it's also a frontier, and tonight, as you rest and listen, you can imagine yourself gently moving outward, carried not by rocket engines or solar sails, but simply by thought, by curiosity, and by the quiet comfort of knowing that wherever we go, the sun's light, faint though it becomes, is still the thread connecting us to home. When we think about something ending, the mind naturally imagines a border, a wall, a line in the sand, a door that marks where one thing stops and another begins. But when it comes to the solar system, there is no neat line to draw. There is no invisible fence in space that says this far and no farther. Instead, the edges blur and overlap depending on what you choose to measure. That makes the simple question of where the solar system truly ends one of the most deceptively complicated puzzles in astronomy. At first glance, the easiest answer seems to be the planets. After Neptune, the 8th planet from the Sun, there are no more large worlds in orbit. So perhaps, you might think, the solar system ends there. Neptune orbits at an average distance of about 30 astronomical units from the Sun. 1 astronomical unit, or a U, is the distance from Earth to the Sun. At Neptune's range, that's 30 times farther out than our own orbit. It seems logical to mark the end there, but as we now know, there are countless smaller bodies beyond Neptune, each carrying their own claim to being part of the Sun's extended family. The discovery of Pluto in 1930 first hinted that the planetary lineup wasn't the whole story, and later discoveries of many more icy worlds only reinforced the idea. If not Neptune, then what? Some suggest the edge is the Kuiper Belt, a vast disk of icy debris stretching from about 30 to 50 AU. The Kuiper Belt contains objects like Pluto, Eris, Haumea and Makemake, all dwarf planets recognised in their own right, along with thousands of smaller bodies. For decades, astronomers believed Pluto was an oddball, a lone icy world at the fringe. Now it's clear it was simply the brightest representative of a much larger population. If you include the Kuiper Belt as part of the solar system, then the boundary stretches farther than Neptune, but still nowhere near the true outer limit. Beyond the Kuiper Belt, there is the scattered disk. Objects there, unlike those in the relatively flat and orderly belt, move on highly elongated orbits that carry them hundreds of AU from the Sun. These scattered worlds, like Eris, stretch the solar system's territory still farther. One such object is Sedna, discovered in 2003. Sedna's orbit is so vast it takes more than 11,000 years to circle the Sun once. At its closest approach, it comes within about 76 AU, already more than twice as far as Pluto. But at its most distant, Sedna retreats nearly 1,000 AU away, into a realm so far beyond the planets that the Sun is just another bright star in the sky. Sedna's orbit raises questions of its own. Did it form there, or was it nudged into place by the gravity of a passing star long ago? Is it part of a population we've barely glimpsed? If so, then the solar system's edge stretches into territory we've scarcely begun to chart. But planetary orbits and icy reservoirs aren't the only way to define a boundary. Another way is through the Sun's influence in space. The Sun is not only a source of light and heat, it also emits a continuous stream of charged particles known as the solar wind. This flow extends outward in all directions, creating a bubble in the interstellar medium called the heliosphere. Inside this bubble, the solar wind dominates. Beyond it, the particles of interstellar space take over. The outer edge of this bubble is called the heliopause, and it is another candidate for the true edge of the solar system. Voyager 1, launched in 1977, reached the heliopause in 2012. At that point, it was about 121 AU from the Sun, nearly 4 times as far as Neptune. Scientists knew the crossing had happened because the spacecraft's instruments recorded a change in the environment. The density of charged particles increased, the magnetic fields shifted, and the faint hiss of plasma waves from interstellar space could be heard. Voyager had left the region dominated by the Sun's wind and entered a new realm. In that sense, it had crossed a meaningful boundary. Yet even there, it was still within the Sun's gravitational influence. Gravity extends farther than the heliosphere. The Sun's mass holds every planet in orbit and every comet in reserve. Even at thousands of AU, the Sun's pull persists, weaker with distance but never quite vanishing. At some point, though, other stars begin to compete. Beyond a certain range, the gravity of passing stars and the general tidal field of the galaxy become just as important as the Sun's. This zone, where the Sun's dominance ends, is another possible definition of the solar system's edge. Astronomers estimate that this boundary lies at about 100,000 AU, nearly 1.5 light-years from the Sun. That's about a quarter of the way to the nearest star system, Proxima Centauri. If that definition is used, then the solar system is staggeringly vast, far larger than most people imagine. Somewhere in that distant realm lies the Oort Cloud, a hypothetical shell of icy bodies surrounding the solar system. Though we've never directly observed it, its existence is inferred from the paths of long-period comets. These comets appear from all directions in the sky, not confined to the flat plane of the planets, suggesting they come from a spherical distribution. The Oort Cloud may contain trillions of icy fragments, leftovers from the formation of the planets, scattered outward by the gravitational jostling of Jupiter and Saturn in the early days. If real, the Oort Cloud marks the outermost region of the Sun's influence. It may extend from about 2,000 AU all the way to that 100,000 AU mark, or even beyond. If the Oort Cloud belongs to the solar system, then the edge is so far away it makes the space between Earth and Neptune feel like a short stroll. And yet, there's still another way to define things. Instead of asking where the Sun's gravity stops or where the solar wind fades, we could ask whether materials that were born from the Sun's formation still remain. The solar system, after all, is the remnant of a molecular cloud that collapsed 4.6 billion years ago. The Sun ignited in the centre, the planets formed from a disk of gas and dust, and leftovers were flung outward. Every comet in the Oort Cloud is a fossil from that process. If even those ancient relics are counted as belonging, then the solar system's true extent is defined by its history, not by any physical boundary in the present. In that sense, the solar system ends wherever its last fragment of birth material still drifts. That could be millions of years away from ever being measured precisely. So when people ask, where does the solar system truly end, the answer depends on the perspective. If you mean the planets, the end is Neptune. If you mean the Kuiper Belt, it's about 50 AU. If you mean the scattered disk, it stretches hundreds of AU. If you mean the heliopause, it's around 120 AU. If you mean the Oort Cloud, it could be tens of thousands of AU, even up to a light year. And if you mean the sun's gravitational hold, it extends until the galaxy itself takes over. Each answer is true in its own way. Each describes a different layer of reality. The solar system does not have one edge but many, nested within one another like the rings of a tree. That makes the question less about finding a single boundary, and more about exploring how the sun shapes its surroundings. The solar system is not a box. It is an influence, a reach, a domain. It stretches outward in light, in wind, in gravity, and in memory. Wherever those influences can still be traced, the solar system continues. And so, the edge is not a wall but a fading, a slow giving way from one kind of dominance to another, from the sun's control to the galaxies, from what belongs to us to what belongs to everything else. For now, the farthest marker we've touched with our machines is the heliopause. Voyager 1 and Voyager 2, both more than 4 decades into their journeys, are the only emissaries that have crossed it. They are still sending back signals, faint whispers carried across billions of miles. They tell us what the space beyond is like, and in doing so, they show us that the question of the edge is not an abstract one. It's something we can measure, something we can touch with the tools we build, and yet beyond them lies more, much more. The Oort Cloud remains unseen, the sun's farthest reach remains unmeasured, the true end remains a matter of definition, and so the solar system does not end in a simple way. It fades, layer by layer, into the wider galaxy. Each layer tells a different story about what it means to belong. Planets, comets, winds, gravity, history. Each definition is useful, but none is final. The edge is both closer and farther than you think, depending on how you look. That makes it not just a scientific puzzle, but a reminder of how categories we create are often only approximations of a reality that refuses to be simple. When people picture a map of the world, the borders are often what stand out most clearly, lines separating countries, shading marking regions, boundaries showing where one place ends and another begins. But those borders, for all their neatness on paper, don't exist as physical walls on the ground. The land rolls on, rivers flow, mountains rise, forests stretch, and the sky passes overhead without interruption. A border is something humans decide to draw, not something nature provides. The solar system is not so different. When we ask where it ends, we're really asking where to draw our lines. Unlike Earth, where borders can be measured in meters or miles, in space the scales are vast and the boundaries are invisible. They're defined not by fences but by forces, by the limits of light, of wind, of gravity, of orbits. They're thresholds you only notice when you measure carefully or send a spacecraft far enough to feel the change. One of the most obvious borders is the one made by planetary orbits. For centuries, astronomers looked at the sky and mapped the motions of wandering stars, the planets. They found a pattern: Mercury close in, then Venus, Earth, Mars, a gap filled with asteroids, Jupiter, Saturn, Uranus, Neptune. That seemed to be the whole story. Once the 8th planet was discovered, many assumed the planetary system must stop there. After all, no bright wanderers were seen beyond it. That invisible border lasted until Pluto's discovery in 1930. Suddenly, Neptune was no longer the final outpost. The line shifted outward. Later still, when astronomers began to uncover more objects like Pluto, the neat border dissolved further. The Kuiper Belt, revealed in the 1990s, showed that the solar system didn't end with one icy dwarf. It extended into a wide zone filled with countless small worlds. The act of drawing a border at Neptune or Pluto no longer made sense. The space beyond was populated, structured, and undeniably part of the Sun's domain. Another border can be drawn by light. The farther you travel from the Sun, the dimmer it becomes. At Earth, sunlight is bright enough to warm the planet, power photosynthesis, and dazzle our eyes. At Mars, the sunlight is weaker but still recognizable. By the time you reach Jupiter, it is only a fraction as intense, casting softer shadows, illuminating moons in a dim glow. Farther out at Neptune, the Sun is just a brilliant star in the sky, its warmth reduced to a thin trickle. Beyond that, in the Kuiper Belt and scattered disk, the Sun is no longer the blazing presence we know, but a pinprick of light. It is still the brightest object in the sky, but only barely. If you choose to define the solar system by where the Sun's light can still shape conditions, the border is another line, fading into darkness where starlight from the galaxy becomes just as important. The solar wind draws yet another invisible boundary. Flowing outward at hundreds of kilometers per second, the charged particles race away from the Sun, filling the heliosphere. The wind creates a bubble around the solar system, pushing against the material that floats between the stars. This bubble isn't static. It breathes, swelling when the Sun is active, shrinking when the solar cycle quiets down. Somewhere near the edge of this bubble, the solar wind slows, piles up, and finally yields to the interstellar medium. That transition is the heliopause, an invisible border that Voyager 1 and Voyager 2 have both crossed. Beyond it, the Sun's breath no longer dominates. If you define the solar system by the reach of its wind, that is where it ends. But gravity insists on another story. The Sun's pull doesn't stop at the heliopause. Every planet and comet is held in orbit by that pull, however faint it becomes with distance. Gravity follows an inverse square law, growing weaker with the square of the distance, but it never truly disappears. Even light years away, the Sun still exerts a tug. The practical question is when the Sun's influence is overtaken by the galaxies. Passing stars, galactic tides, and the overall gravitational field of the Milky Way slowly strip away the farthest objects. That point where the Sun's grip is no longer the strongest is another border. Though one so diffuse it's almost impossible to mark cleanly, estimates place it at around 100,000 astronomical units, but there is no fence post there, only a gradual fading. The Oort Cloud, if it exists as predicted, is another kind of border, not one drawn by physics alone, but by population. The Oort Cloud would be a spherical shell of icy bodies, scattered in every direction. They are too small and too far to be seen directly, but the comets that fall inward from time to time betray their presence. Long-period comets, with orbits lasting millions of years, must come from a reservoir beyond the planets and the Kuiper Belt. The Oort Cloud is the best explanation. If you consider every object born from the Sun's nursery to be part of its system, then the solar system ends at the outer edge of this vast shell. That could be a light year away, perhaps more. It means the solar system's invisible border reaches halfway to the nearest star. Astronomers sometimes talk about the Hill sphere, another measure of influence. The Hill sphere is the region where an object's gravity dominates over the pull of a larger body it orbits. Earth has a Hill sphere, defining where it can hold on to moons and satellites against the Sun's pull. The Sun, in turn, has a Hill sphere with respect to the galaxy. That sphere marks where the Sun's gravity rules over the Milky Ways. Its radius is roughly the same as the predicted edge of the Oort Cloud. So once again, a different method of calculation draws a line in nearly the same place. It is one more way to imagine the solar system's border, though just like the others, it's not visible or sharp. These invisible borders overlap like layers. If you draw them all together, you get a picture of the solar system, not as a tidy circle, but as a set of concentric zones, each fading into the next. The planetary zone is one border. The Kuiper Belt is another. The heliopause adds its own. The Oort Cloud stretches beyond, and the Hill sphere marks the outer gravitational limit. None of these are wrong. They are simply different ways of answering the same question. And yet, each border has meaning. For spacecraft, the heliopause is a real crossing, a shift from one environment to another. For comets, the Oort Cloud is a reservoir that defines their origin. For planets and moons, the Hill sphere explains why they orbit the bodies they do. These borders may be invisible, but they shape the architecture of the solar system. They help us understand how the Sun fits into the wider galaxy. It's interesting to notice how much these borders depend on perspective. If you lived on Neptune, you might think the solar system ends with your orbit. If you were an icy fragment in the Kuiper Belt, you'd see yourself as part of a community extending far beyond Pluto. If you were Voyager 1, crossing the heliopause, you'd report back that the solar system ended there. And if you were a long-period comet drifting in the Oort Cloud, you'd still be part of the Sun's family, bound by gravity across light years. Each vantage point gives a different answer. The act of drawing borders is really an act of definition. It tells us more about what we value or what we measure than about the cosmos itself. Nature rarely offers clean lines. Instead, it offers gradients, transitions, and continua. The solar system is a perfect example. It is a structure with no walls, only influences that weaken with distance. We carve it up into zones so we can study and understand it, but those zones are human tools, not natural boundaries. As exploration continues, these invisible borders may shift again. The discovery of Sedna and other distant objects hinted at another possible population between the scattered disk and the Oort Cloud. Some astronomers suggest an inner Oort Cloud, or even a hidden planet shaping those orbits. If such a body exists, then our idea of the border would stretch once again. The discovery of new physics, or better measurements of the Sun's outer influence, could redraw the lines too. The solar system is not fixed on paper. It is alive with mystery, and our maps evolve as we learn. So when we think about the solar system's end, it helps to let go of the idea of a single frontier. Instead, think of it as a set of overlapping borders, each invisible but real in its own way. Borders of light, of wind, of orbit, of gravity. Borders marked not by fences but by change. The solar system doesn't end abruptly. It fades, layer by layer, into the galaxy beyond. And as we follow those layers outward, the question is not only how far the solar system goes, but how many different ways we can define belonging to it. When people first learn about the solar system, it's the planets that usually come to mind. The great celestial bodies orbiting the Sun, each with its own character, its own rhythm, and its own history. They're the most familiar landmarks of the system, the ones we've studied for centuries, the ones visible even to the naked eye on clear nights. They form the core of our picture of what the solar system is, a kind of central stage where most of the action seems to happen. And while the planets are only a small part of the Sun's full domain, they give us a grounding point. By understanding them and the paths they take, we begin to appreciate what it means for the solar system to be a system at all. Mercury is the closest, a world so near the Sun that it never strays far from the glare. Its orbit is the fastest of them all, whipping around in just 88 Earth days. To an observer standing on its rocky surface, the Sun would loom enormous in the sky, 3 times larger than what we see from Earth. Mercury's path is not a perfect circle. It's slightly elongated, and its motion was once one of the great puzzles of astronomy. For centuries, astronomers noticed that Mercury's orbit shifted more than Newton's laws predicted. The discrepancy was small, but persistent. It wasn't until Einstein introduced general relativity that the puzzle was solved. The curvature of space-time around the Sun accounted for the extra motion, and Mercury's path became one of the first confirmations of Einstein's theory. In this way, the smallest planet played a role in proving one of the biggest breakthroughs in science. Next is Venus, nearly Earth's twin in size and mass, but so very different in nature. Venus orbits the Sun in 225 Earth days, and unlike most planets, it rotates in the opposite direction, slowly turning backward compared to its orbit. A day on Venus, measured by the time it takes for the planet to spin once on its axis, lasts longer than its year. Its orbit is almost perfectly circular, keeping it at a consistent distance from the Sun. Because of its brightness, Venus has been called the morning star or the evening star, depending on when it appears. Ancient civilizations tracked it carefully, weaving it into myths and calendars. Its path across the sky is one of the most reliable patterns visible from Earth, though the planet itself, hidden beneath thick clouds of sulfuric acid and carbon dioxide, is far from hospitable. Its orbit tells us about resonance, balance, and how a planet so similar in size to ours can be utterly alien in nature. Then comes Earth, our home, circling the Sun once every 365 days. Its orbit is nearly circular as well, with just enough eccentricity to create the seasons we experience. The tilt of Earth's axis, about 23.5 degrees, means that as the planet travels along its path, sunlight falls more directly on one hemisphere and then the other. This simple geometric relationship, Earth's orbit and its tilt, gives rise to the cycle of winter and summer, planting and harvest, darkness and light. For us, the solar system's architecture is not abstract. It governs daily life, shaping climate, biology and culture. Earth's orbit is the anchor for our sense of time, the basis of calendars, festivals and traditions. To know the planet's path is to know why a year feels the way it does. Mars follows next, a little farther out, circling the Sun once every 687 Earth days. Its orbit is more elongated than Earth's, giving it more variation in distance from the Sun. When Mars is closest to Earth, opposition as astronomers call it shines brightly in the night sky, glowing with its distinctive reddish hue. The planet's orbit has long been a testing ground for our understanding of celestial mechanics. Johannes Kepler, in the early 1600s, used detailed observations of Mars to discover that planetary orbits are ellipses, not circles. That insight revolutionized astronomy, replacing ancient ideas of perfect spheres with a geometry that matched reality. Mars, with its wandering motion against the stars, helped unlock the mathematical description of planetary paths that we still use today. Beyond Mars lies the asteroid belt, a region filled with rocky fragments that never coalesced into a full planet. But just beyond that, the solar system changes character. Jupiter, the largest of all, dominates the outer region. Its orbit takes nearly 12 Earth years, and its mass is more than twice that of all the other planets combined. Jupiter's path is nearly circular, steady and immense, but its influence reaches much farther than its orbit alone. Its gravity shapes the asteroid belt, carving gaps where orbital resonances prevent objects from remaining stable. It captures comets, redirects asteroids, and even protects the inner planets by sweeping up or deflecting potential impactors. To study Jupiter's orbit is to study a balance of stability and disruption. It is both guardian and scatterer, a planet whose path defines much of the solar system structure. Saturn, with its elegant rings, comes next, orbiting the Sun every 29 years. Its path is wide, more than 1 billion kilometers from the Sun, and its gravitational reach is immense. Saturn's orbit, like Jupiter's, is close to circular, a steady course that belies the complexity of the system around it. Dozens of moons accompany Saturn, each with its own smaller orbit, creating a miniature solar system within the larger one. The resonances between Saturn's moons and between Saturn itself and Jupiter play a role in shaping the broader architecture of the solar system. These giant planets are not just passive travellers. Their orbits interact, sculpt and maintain the dance of smaller bodies. Uranus, tilted so far on its side that it essentially rolls along its orbit, circles the Sun every 84 years. Its distance is staggering, nearly 20 times farther from the Sun than Earth. From Uranus, the Sun is a small but brilliant star, and the seasons last for decades. Because of its extreme tilt, each pole spends about 42 years in continuous sunlight, followed by 42 years in darkness. Its orbit is another near circle, but its orientation makes the experience of that orbit unlike anything closer in. Uranus's path shows how even within the same system, planets can follow the same basic rules yet create entirely different realities. Neptune is the final giant, orbiting the Sun once every 165 years. Its discovery was itself a triumph of orbital mechanics. Astronomers noticed irregularities in Uranus's path, small deviations from prediction, and realized another planet must be tugging at it. By calculating where such a planet would need to be, they predicted Neptune's existence before it was ever seen. When it was finally observed in 1846, it confirmed not only the planet itself, but the power of mathematics to reveal unseen worlds. Neptune's orbit is nearly circular, like the other giants, but its influence is complex. It resonates with Pluto, keeping the smaller world in a stable 3.2 orbital pattern. Pluto, though crossing Neptune's path in projection, never collides because of this resonance. The precision of these paths, playing out over millions of years, shows how stability can emerge from apparent chaos. Pluto, Eris, Haumea, Makemake, and the other dwarf planets follow still wider, elongated orbits. Their paths are reminders that the solar system is not made only of neat circles. Many of these orbits stretch into long ellipses, carrying them close to Neptune at one point and far beyond at another. Their rhythms are slower, their years far longer, their movements harder to predict without careful calculation. These orbits are where the orderly world of planets begins to fade into the more chaotic realm beyond. What unites all these paths, from Mercury's quick whirl to Neptune's slow crawl, is that they follow the same underlying principle. They are bound by gravity, moving not in straight lines, but in curves around the Sun. Kepler's laws describe their shapes, Newton's laws describe their motions, and Einstein's relativity adds subtle corrections at the extremes. Together, these orbits create the solar system's architecture, a set of invisible highways traced over billions of years. Each planet follows its lane, influenced by its neighbours but steady enough to keep order across vast timescales. The familiar planets and their paths give us the framework for understanding where we are. They mark the inner zones, the middle reaches, and the outer giants. They show us that even within the solar system, distance scales vary enormously. The difference between Earth and Mars feels large to us, but compared to the gulf between Jupiter and Neptune, it is small. These paths remind us that the solar system is not a compact family but a sprawling one, with members spread across enormous distances. When the early catalogue of the planets was thought to be complete, Neptune seemed like the last word. It was far away, mysterious, difficult to see without a telescope, and yet its existence was proven by mathematics before it was ever confirmed by the eye. To many that felt like the natural frontier, 8 planets circling the Sun, each progressively farther out, with Neptune as the silent sentinel marking the edge. But the universe rarely aligns itself with the neatness of our expectations. Just beyond Neptune, the story only begins to grow stranger. The region past Neptune is not a tidy void. It is filled with icy worlds, dark fragments, and faint travellers that defy simple categorization. This expanse is what astronomers came to call the Kuiper Belt, a disk of icy debris stretching outward from about 30 to 50 astronomical units. For scale, 1 astronomical unit is the distance between Earth and the Sun, about 93 million miles. Multiply that by 50, and you're already at distances so great that the Sun, though still the brightest object, is more like a dazzling star than a blinding disk. Within this space, light weakens, warmth diminishes, and the familiar glow of the inner planets becomes a memory. For a long time, Pluto stood as the lone representative of this frontier. Discovered in 1930, it was hailed as the 9th planet. But Pluto is small, smaller than Earth's moon, with a thin atmosphere that freezes onto its surface when it drifts farther from the Sun. Its elongated orbit carries it inside Neptune's path at times, then back out again. For decades, Pluto seemed like an odd outlier, a curiosity at the edge. Only later did astronomers realise that Pluto was not alone. In the 1990s, improved telescopes began to reveal a multitude of small icy bodies beyond Neptune. These discoveries confirmed what a Dutch-American astronomer, Gerard Kuiper, had predicted decades earlier, though the details were different. The Kuiper Belt turned out to be a vast population of objects, perhaps hundreds of thousands larger than 100 kilometres across, and many more smaller fragments. Pluto was simply the brightest, a standout in a crowded neighbourhood. Suddenly, Neptune no longer looked like the end. It was a gateway into a new region. These worlds are faint, hard to detect, and most of them remain nameless numbers in astronomical surveys. Yet each one is a relic from the solar system's formation, a frozen remnant that never grew large enough to become a planet. Their orbits vary. Some move on nearly circular paths, others on more eccentric tracks. Some are locked in resonances with Neptune, meaning their orbits are shaped and stabilized by gravitational relationships with the giant planet. Pluto itself is in a 3.2 resonance, orbiting the Sun twice for every 3 times Neptune does. This resonance prevents collisions, keeping Pluto's elongated orbit stable over billions of years. Beyond the main Kuiper Belt lies an even stranger population, the scattered disk. These are objects whose orbits have been stretched and distorted, often by past interactions with Neptune, or possibly even with passing stars. Scattered disk objects travel on elongated ellipses that carry them far beyond the belt, hundreds of astronomical units into the dark. Their orbits are unstable on long time scales, slowly shifting due to the tug of gravity. One of the most intriguing members of this group is Eris, discovered in 2005. Eris is slightly smaller than Pluto but more massive, and its discovery forced astronomers to reconsider the definition of a planet. The debate ultimately led to Pluto's reclassification as a dwarf planet, joining Eris, Haumea, Makemake and others in a new category. The presence of the scattered disk highlights that the solar system does not simply taper off. Instead, it becomes more chaotic. Orbits stretch, populations thin, and the sense of order we see in the planetary system gives way to irregularity. The scattered disk is like a transitional zone, leading outward to even greater distances where objects are only loosely bound. Among the scattered bodies, one stands out for its peculiarity: Sedna. Discovered in 2003, Sedna follows an orbit that takes it to a perihelion, or closest approach to the Sun, of about 76 AU. That alone is extraordinary, but its aphelion, or farthest point, extends close to 1000 AU. One orbit takes more than 11,000 years to complete. Sedna spends most of its existence in darkness, so far from the Sun that even at its closest the warmth is negligible. Its discovery raised new questions. How did an object end up on such an orbit, too distant to be explained by Neptune's influence alone? Some theories suggest Sedna may have been nudged into place by a passing star in the early days of the solar system, when the Sun was still in a stellar nursery surrounded by other stars. Others suggest the presence of an as-yet undiscovered massive planet, sometimes called Planet 9, lurking far beyond Neptune. The search for Planet 9 remains ongoing. Astronomers have noted that the orbits of several distant scattered disk objects appear to cluster in a way that hints at the gravitational pull of something unseen. If such a planet exists, it could be 10 times the mass of Earth, orbiting hundreds of AU away. Its presence would reshape our understanding of the solar system's architecture, expanding its known structure and adding a new giant to the family. Whether Planet 9 is real, or whether the clustering is a coincidence, is still debated, but the very possibility shows how incomplete our map of this region remains. Beyond the scattered disk, theorists place the inner edge of the Oort Cloud. the vast spherical shell of icy bodies that may extend tens of thousands of AU. But unlike the Kuiper Belt and scattered disk, the Oort Cloud has never been directly observed. Its existence is inferred from the behaviour of comets. Long-period comets, those that take hundreds of thousands of years to orbit the Sun, appear from all directions, not just along the plane of the planets. Their arrival suggests a reservoir that surrounds the solar system in every direction. If the Oort Cloud is real, it marks the ultimate realm of shadows, where the Sun's influence is stretched to its outermost limits. What makes this region beyond Neptune so compelling is that it shifts our sense of scale. Within the planetary system, distances are already immense. Neptune itself is 30 times farther from the Sun than Earth. But the scattered disk and beyond operate on scales of hundreds or thousands of AU. Suddenly, even Neptune feels close. The units we use, the familiar astronomical unit, start to seem inadequate. Light, which takes 8 minutes to reach Earth from the Sun, takes over 4 hours to reach Neptune. To reach Sedna at its farthest, it takes more than a week. To reach the edge of the Oort Cloud, it may take a year. These are distances where our normal intuitions falter. Another striking aspect of this region is its darkness. Sunlight, by the time it reaches the Kuiper Belt, is 1,000 times weaker than at Earth. At Sedna's distance, it is tens of thousands of times weaker. Shadows dominate, broken only by faint starlight and the dim glow of the Sun as just another point in the sky. For spacecraft travelling outward, this region poses challenges. Solar panels become ineffective. Communication takes hours, then days. Instruments must rely on radioisotope power rather than light. Voyager, New Horizons, and other distant probes remind us that exploration here is slow and fragile. And yet, these shadows are not empty. They hold the history of the solar system. The icy worlds and fragments beyond Neptune are leftovers from the solar system's birth. They preserve the composition of the early disk of gas and dust, untouched for billions of years. Studying them, even from afar, helps scientists reconstruct how the planets formed, how giant planets migrated, and how comets came to deliver water and organics to Earth. In that sense, the realm beyond Neptune is not just a shadowy frontier but an archive, a record of deep time. Each discovery here reshapes our map. Pluto, once unique, became one of many. Eris, once just another faint point, forced a redefinition of planets. Sedna hinted at unseen influences. The possibility of Planet 9 challenges our sense of completeness. The scattered disk and Oort Cloud, though still largely theoretical, show that the solar system's influence extends farther than most ever imagined. The shadows beyond Neptune are not a boundary but an invitation to keep looking. As we continue outward in thought, this realm becomes less about familiar planets and more about populations, reservoirs and transitions. It is not the orderly system of orbits we see inside, but a place where orbits stretch, cross and wander. It is where the Sun's presence is still felt but faintly, like an echo. To pass through it is to leave the bright heart of the solar system behind and begin to drift into the uncertain territories that connect us to the galaxy beyond. When you imagine the solar system, it is easy to picture the Sun in the centre, the planets in their wide orbits, and perhaps a scattering of comets flying through. But that image leaves out one of the most significant regions of all, a band of icy bodies stretching far beyond the planets, circling the Sun in a wide ring. This is the Kuiper Belt, a frozen frontier that quietly reshaped our understanding of what the solar system really is. The Kuiper Belt begins just past Neptune, around 30 astronomical units from the Sun, and extends outward to about 50. Within that span, countless icy bodies orbit, most of them small, some of them large enough to be called dwarf planets. For decades, Pluto was thought to be the oddball at the edge, a lone world wandering far from the others. The truth turned out to be much more complicated. Pluto is not an outlier. It is a member of a vast population. The discovery of the Kuiper Belt in the 1990s was one of the most important astronomical breakthroughs of the 20th century. It confirmed that the solar system is not just a tidy set of planets, but a layered structure with populations of objects at different distances. The Kuiper Belt is often compared to the asteroid belt, but it is much larger and much more massive in its early days. While the asteroid belt lies between Mars and Jupiter and is rocky in nature, the Kuiper Belt lies far beyond Neptune and is icy, filled with frozen water, methane, nitrogen, and other volatile compounds. The two belts share the characteristic of being leftovers, remnants from the solar system's formation that never formed into planets. The objects in the Kuiper Belt vary widely. Some are just a few kilometers across, icy fragments drifting through space. Others are hundreds, or even over 1,000 kilometers in diameter, large enough to be spherical under their own gravity. Pluto, Eris, Haumea and Makemake are the best known, but they are only the beginning. Many more likely remain undiscovered, hidden in the dark, too faint for current telescopes to see. The orbits of Kuiper Belt objects are shaped by Neptune. Many are in resonance with the giant planet, meaning their orbital periods have simple ratios with Neptune's. Pluto's in a 3.2 resonance, completing 2 orbits for every 3 of Neptune's. This resonance keeps Pluto's orbit stable, preventing close encounters with Neptune even though the two paths cross in projection. Other Kuiper Belt objects share similar resonances, forming families of stable orbits that endure over billions of years. Without Neptune's influence, many of these orbits would not survive. There are different categories within the Kuiper Belt. Classical Kuiper Belt objects, sometimes called cubewanos after the first one discovered, orbit in relatively circular stable paths between about 42 and 48 AU. Resonant objects like Pluto are locked in orbital patterns tied to Neptune. Scattered objects, often grouped separately, have orbits stretched by past encounters with Neptune, and sometimes reach far beyond the belt. Together, these categories form a complex and dynamic structure, a frozen frontier shaped by gravity. The Kuiper Belt also plays a role in the story of comets. Many short-period comets, those that orbit the Sun in less than 200 years, are believed to originate in this region. Gravitational nudges can send them inward, where they develop tails of gas and dust as they warm near the Sun. Each comet that lights up the night sky is a messenger from the Kuiper Belt, carrying material unchanged since the dawn of the solar system. Studying Kuiper Belt objects is difficult. They're far away, small and dark. Most reflect little sunlight, making them faint points even in powerful telescopes. Direct exploration is rare. The New Horizons mission, launched in 2006, gave us our first close-up look at Pluto and its moons in 2015. The images revealed a world far more complex than expected, with mountains of ice, glaciers of nitrogen, and a thin but active atmosphere. Pluto was no frozen relic. It was geologically alive, reshaping itself in ways that challenged assumptions. After Pluto, New Horizons continued into the Kuiper Belt, flying past Arakoth, a contact binary object about 30 kilometers across. Its shape, resembling 2 lobes gently pressed together, suggested that Kuiper Belt bodies may have formed by slow accretion, merging gently rather than through violent collisions. These glimpses are only the beginning. The Kuiper Belt likely holds vast diversity, with objects shaped by different conditions, compositions, and histories. Some may contain clues to the migration of the giant planets. Models suggest that Jupiter, Saturn, Uranus, and Neptune did not form exactly where they are now. They shifted positions in the early solar system, scattering icy planetesimals outward and inward. The Kuiper Belt, in this view, is a fossil record of that migration, a collection of bodies left behind in resonances and stable niches. By studying it, scientists hope to reconstruct the solar system's evolution. One of the most striking aspects of the Kuiper Belt is its sheer scale. From Earth to Neptune is already an enormous distance, but the Kuiper Belt spans a region as wide as the distance between the Sun and Neptune itself. Within that span, billions of icy bodies orbit in silence. too faint to see, too small to dominate, yet collectively forming a structure that rivals the planets in importance. It is a frontier not in the sense of being empty, but in being filled with mysteries yet to be revealed. There is also a cultural side to the Kuiper Belt story. Pluto's reclassification in 2006 from planet to dwarf planet was a direct consequence of the discoveries made here. Once Eris was found, slightly larger than Pluto, it became clear that either Pluto's status had to be reconsidered or dozens of new planets would need to be added. The decision to create the category of dwarf planets reflected the need for clarity, but it also sparked debate and emotion. For many, Pluto's demotion felt personal. It highlighted how our definitions are as much about human categories as about nature itself. The Kuiper Belt showed that the solar system is more complicated than the simple lineup of planets taught in childhood, and that complexity forced us to rethink. Even now, the Kuiper Belt is not fully mapped. Large telescopes, like the Subaru telescope in Hawaii and the Vera Rubin Observatory being built in Chile, continue to survey the sky, searching for faint moving points that betray new members. Each discovery adds to the census, revealing new orbital patterns, new resonances, new clues. It is a slow process because these objects move so gradually against the stars. Tracking them takes years. But patience yields results, and the picture of the frozen frontier grows clearer. The Kuiper Belt is also where speculation about unseen influences arises. Some of the most distant Kuiper Belt objects have orbits that seem clustered in ways that suggest a massive planet beyond, pulling on them with its gravity. This is the basis of the Planet 9 hypothesis. If such a planet exists, it would redefine the Kuiper Belt once again, extending its structure into an even broader system. Whether or not Planet 9 is real, the fact that the Kuiper Belt leads us to such questions shows how incomplete our knowledge remains. For all its distance, the Kuiper Belt is connected to us. Comets from its population visit the inner solar system, sometimes visible to the naked eye. Missions like New Horizons send back images and data, and telescopes continue to expand our awareness of its diversity. The frozen frontier may seem remote, but it is part of the same system that includes Earth, bound by the same sun. The difference is only scale and perspective. The Kuiper Belt represents a transition. Inside it, the solar system feels ordered, with planets moving in nearly circular paths. Beyond it, in the scattered disk and Oort Cloud, orbits become elongated and irregular. The Kuiper Belt is the middle ground, structured but stretched, stable but influenced. It is the bridge between the familiar planetary system and the more chaotic outer regions. To understand it is to understand not only where the solar system's boundary lies, but how it changes character as you move outward. For much of the 20th century, Pluto held a special place in the human imagination. Discovered in 1930 by Clyde Tombaugh, it was hailed as the 9th planet, the tiny outpost at the edge of the Sun's domain. Generations of schoolchildren memorized its name at the end of the list, often attaching a kind of affection to it because it seemed like the odd little sibling in a family of giants. It was distant, cold, and mysterious, a place that almost nobody expected we would ever see up close. For decades, Pluto stood alone, but as our telescopes grew stronger and our surveys more systematic, it became clear that Pluto was not an isolated wanderer, but part of a much larger population. That realization changed its status, redefined what it meant to be a planet, and introduced us to the idea of a family of dwarf worlds. Pluto's orbit is unusual compared to the 8 classical planets. It takes about 248 Earth years to complete a single trip around the Sun, and its path is elongated, ranging from about 30 astronomical units at its closest to nearly 50 at its farthest. Unlike the planets, whose orbits lie in a relatively flat disk, Pluto's orbit is tilted about 17 degrees relative to the ecliptic. That tilt, along with the elongated shape, means Pluto crosses Neptune's orbit when viewed in projection. But Pluto is not at risk of colliding with Neptune. Its orbit is locked in a resonance, completing 2 orbits for every 3 of Neptune's. This resonance ensures stability, keeping the 2 worlds safely separated over billions of years. It is one of many examples of how gravitational interactions create order in what might otherwise seem chaotic. Pluto also has moons, the largest of which, Charon, is so big relative to Pluto that the 2 form a kind of double system. Charon is about half the size of Pluto, and the centre of mass around which they orbit lies outside Pluto itself. To an observer, it looks less like a planet with a moon and more like a binary pair. Charon's presence has profound effects on Pluto, creating tidal interactions that influence its rotation and internal structure. In addition to Charon, Pluto has 4 smaller moons, Styx, Nix, Kerberos and Hydra, all discovered in the early 21st century. These moons are irregularly shaped, likely captured or fragments from collisions, adding to the complexity of Pluto's system. For decades, Pluto remained only a faint dot in telescopes, its surface features blurred beyond recognition. That changed with the arrival of the New Horizons mission in 2015. After a 9-year journey across the solar system, New Horizons flew past Pluto and returned the first detailed images. What it revealed was astonishing. Pluto was not a dead frozen rock. It was geologically active. Vast plains of nitrogen ice stretched across its surface. Mountains made of water ice towered like frozen Alps. A massive heart-shaped feature named Tombor Regio after its discoverer became a symbol of the mission. Craters were present but unevenly distributed, suggesting some areas of the surface had been reshaped recently in geological terms. There were signs of glaciers, sublimation, and possible cryovolcanism. An atmosphere of nitrogen, thin and tenuous, extended hundreds of kilometers above the surface, with layers of haze that scattered sunlight into delicate blues. Pluto turned out to be a world of complexity and beauty, far beyond what anyone had expected. New Horizons showed that Pluto was not just another icy body, but a dynamic, evolving world. Yet by that time, Pluto had already been reclassified. In 2006, the International Astronomical Union defined the term planet more strictly. To be a planet, a body must orbit the Sun, be massive enough for gravity to make it nearly spherical, and have cleared its orbital neighbourhood of other debris. Pluto met the first 2 criteria, but not the third. Its orbit overlaps with countless Kuiper Belt objects. Because of that, Pluto was redefined as a dwarf planet. The decision was controversial, sparking debate both within astronomy and among the public. For many, Pluto's demotion felt like the loss of a childhood friend. But scientifically, the reclassification reflected a deeper truth. Pluto is part of a family, not an exception. That family includes other large Kuiper Belt objects like Eris, discovered in 2005. Eris is slightly smaller in diameter than Pluto, but more massive. Its discovery was a turning point. If Pluto was a planet, then Eris deserved the same status. But if Pluto remained unique, then Eris and many others would force the list of planets to grow dramatically. The creation of the dwarf planet category was a way to acknowledge their importance, without expanding the planet count into the dozens. Eris orbits much farther from the Sun than Pluto, ranging from 38 to 97 AU, and takes 557 years to complete one orbit. Like Pluto, Eris is part of the scattered disk, its orbit influenced by Neptune in the distant past. Another member of the family is Haumea, discovered in 2004. Haumea is one of the strangest bodies in the solar system. It is elongated, shaped more like a football than a sphere, likely due to rapid rotation. Haumea spins once every 4 hours, the fastest rotation of any known large object in the solar system. This rapid spin stretches it into its unusual form. Haumea also has a ring, a rare feature for a small world, and 2 moons, Hi'iaka and Namaka. Its surface is covered in crystalline water ice, suggesting it may have undergone collisions that exposed fresher material from below. Makemake, discovered in 2005, adds another to the roster. Similar in size to Haumea and slightly smaller than Pluto, Makemake has a bright surface covered in methane ice. It takes about 305 years to orbit the Sun and resides in the classical Kuiper Belt. In 2016, a small moon was discovered orbiting Makemake, temporarily nicknamed MK2. These discoveries highlight that even the distant icy dwarfs often have companions, creating small systems within systems. Together, Pluto, Eris, Haumea, and Makemake form the 4 officially recognised dwarf planets in the Kuiper Belt, but they are not the only candidates. Astronomers suspect that dozens more large enough to qualify exist, waiting to be discovered. Some, like Sedna, may occupy transitional regions between the Kuiper Belt and the Oort Cloud. Others may lurk farther out, faint and hidden. The family of dwarf worlds is likely far larger than we currently know. These worlds share certain traits. They are spherical or nearly so, massive enough for gravity to shape them, but too small to clear their orbits. They orbit in distant, icy regions where the sun's warmth is weak. They often have moons, atmospheres, or signs of geological activity. Each is unique in detail, but together they represent a category of worlds that blur the line between planets and smaller bodies. They remind us that the solar system is not neatly divided but filled with gradations. Studying these dwarf planets helps scientists understand the solar system's formation. They are thought to be remnants of the building blocks of planets, planetesimals that never merged into larger bodies. Their compositions preserve the materials of the early solar system, including volatile ices that would have evaporated closer in. Their orbits record the gravitational interactions that scattered them outward, whether from Neptune's migration or from encounters with passing stars. In their surfaces and atmospheres, we see the fingerprints of billions of years of history. For the public, Pluto remains the most beloved, and its reclassification continues to inspire debate. Some scientists argue that the current definition of a planet is too restrictive, that clearing the neighbourhood is not a meaningful criterion. They propose that any spherical body orbiting the Sun should count, which would restore Pluto's status and add many more planets to the list. Others argue that the current definition helps maintain clarity, distinguishing the major planets from the numerous smaller ones. The debate illustrates how science is not only about data, but about the words we use to categorize. Our definitions evolve as our knowledge grows. The family of dwarf worlds also expands the imagination. When people think of exploring the solar system, they often think of Mars, Jupiter's moons, or Saturn's rings. But the dwarf planets offer a different kind of frontier. They are distant, faint and cold, but they hold surprises, like Pluto's active geology or Haumea's ring. Missions to explore them are challenging due to their distance, but the success of New Horizons shows that such missions are possible. In the future, spacecraft may visit Eris, Haumea, or Makemake, revealing more details and perhaps uncovering features we have not even guessed. Beyond their scientific importance, the dwarf planets remind us of the diversity of worlds. The solar system is not composed of 8 neat planets and then empty space. It is filled with gradations, with objects that defy simple categories. Some are nearly planetary in character, others are closer to comets. Together they form a continuum that shows how messy and rich planetary formation can be. By studying them, we broaden our definition of what a world can be. Pluto may no longer be the 9th planet, but it is no less fascinating. Its demotion only highlighted that it belongs to a larger family, one that reshaped our view of the solar system. The family of dwarf worlds shows that there is no sharp boundary between planets and small bodies, only a spectrum. They are the ambassadors of the outer solar system, the stepping stones that lead us from the familiar planets to the distant shadowy regions beyond. When you look at the night sky and see a comet, it can feel like a visitor from another realm. Unlike stars that remain fixed or planets that move predictably along the zodiac, a comet appears suddenly, often with a glowing head and a long tail stretched across the heavens. It can be bright enough to draw crowds into the night, as it has for millennia, or faint enough to require telescopes to find. But always, a comet feels like a messenger, something that does not belong to the ordinary rhythm of the sky. And in a very real way, that's exactly what it is. Comets come from the outer reaches of the solar system, from regions far beyond the familiar planets. They carry with them material that has been preserved since the earliest days of the solar system, 4.6 billion years ago. They are icy time capsules, delivering samples of the distant frontier into the inner solar system where we can see them. To study a comet is to study a fragment of the sun's birth environment, preserved in deep freeze for billions of years. Their sudden appearances are not random, but the result of long journeys along immense elliptical orbits that take them across vast distances. Each comet we see in the night sky has travelled a path that links the frozen edge of the solar system to the warmth of the inner planets. There are two main families of comets. Short-period comets, which orbit the Sun in less than 200 years, are believed to come from the Kuiper Belt. Their orbits are influenced by Jupiter and the other giant planets, gradually nudged inward over time. Long-period comets, with orbits lasting thousands or even millions of years, are thought to originate in the Oort Cloud. This distant reservoir, still hypothetical but strongly supported by the evidence, surrounds the solar system in a vast sphere extending tens of thousands of astronomical units. When a passing star or galactic tide disturbs one of these icy bodies, it can fall inward, spending most of its life in darkness before briefly flaring into visibility near the Sun. The path of a comet is an ellipse, often highly elongated. At its farthest, it may drift so slowly that it takes thousands of years to complete a single orbit. At its closest, it whips around the Sun in a matter of weeks or months. As it approaches the Sun, heat begins to sublimate its ices, turning them directly into gas. Dust is carried along, forming a glowing coma around the nucleus. The pressure of sunlight and the solar wind then push this material outward, creating the iconic tails. One tail is made of dust, reflecting sunlight, often curved as particles follow their own paths. The other is made of ionized gas, glowing faintly blue and always pointing directly away from the Sun due to the solar wind. These tails can stretch for millions of kilometers, making comets some of the most dramatic objects in the sky. Historically, comets inspired awe and fear. Ancient cultures often saw them as omens, heralds of disaster or change. Their sudden appearances disrupted the apparent stability of the heavens, challenging the idea of a perfect, unchanging sky. Records from China, Babylon, Greece, and other civilizations describe comets in detail, often tying them to events on Earth. Even as late as the Middle Ages, comets were viewed with superstition, associated with plagues, wars, or the deaths of kings. It was only in the scientific revolution that comets were recognized as natural celestial objects obeying the same laws as planets. One of the most famous comets is Halley's Comet, named after Edmund Halley, who realized that several bright comets seen in different centuries were in fact the same object returning on a 76-year orbit. Halley's insight showed that comets were not unpredictable apparitions, but members of the solar system with regular paths. Since then, Halley's Comet has become a symbol of recurrence, appearing in 1910 with a spectacular display, and again in 1986, when spacecraft visited it for the first time. Future generations will see it again in 2061. Each return is a reminder of the link between Earth and the far reaches of the solar system. Modern missions have given us even closer looks at comets. The European Space Agency's Rosetta mission, launched in 2004, rendezvoused with comet 67P Churyumov-Gerasimenko in 2014. For over 2 years, Rosetta orbited the comet, studying its surface, activity and composition. It even deployed a small lander, Philae, which touched down on the surface, though in a less than ideal location. The images revealed a strange two-lobed shape, with cliffs, pits and jets of gas erupting as the comet neared the Sun. The composition showed a mixture of water ice, carbon compounds and organics, supporting the idea that comets could have delivered key ingredients for life to the early Earth. NASA's Deep Impact mission in 2005 went further, sending a probe to collide with Comet Tempel 1, creating a plume that allowed scientists to study its interior. The results showed a mixture of ices and dust, loosely bound, more like a pile of rubble than a solid rock. These missions confirm that comets are fragile dynamic bodies, shaped by heat and sunlight during their brief visits to the inner solar system. The study of comets ties directly into the question of distance. Because comets come from the Kuiper Belt and the Oort Cloud, there are only direct samples of those remote regions. When a comet appears, it carries with it the story of where it came from. A short-period comet like Encke or 67P tells us about the frozen frontier beyond Neptune. A long-period comet, appearing suddenly from a random direction in the sky, tells us about the distant Oort Cloud, a region so far away we cannot see it directly. Each comet is a messenger, a traveller across distances we can hardly fathom. The orbits of comets also reveal the solar system structure. By tracking their paths, astronomers can infer the existence of reservoirs. The very fact that comets arrive from all directions suggests a spherical Oort cloud rather than a flat disk. The distribution of short-period comets matches the structure of the Kuiper Belt. Comets are like breadcrumbs left behind, guiding us to regions we cannot yet explore directly. In addition to their scientific importance, comets connect us emotionally to the cosmos. When a bright comet appears, it becomes a shared experience. In 1997, Comet Hale-Bopp lit up the sky for months, visible even in urban areas. In 2020, Comet Neowise surprised observers with a bright tail, offering a rare sight in a modern era of light pollution. People all over the world stepped outside to see it, posting photographs, sharing stories, and feeling for a moment connected to something ancient. The sight of a comet stirs a sense of wonder that goes beyond science, a reminder of our place in a much larger system. The fragility of comets is also part of their message. Some disintegrate as they approach the sun, breaking apart under the stress of heat and gravity. Others fade over time, losing their volatile ices with each pass until they become inert bodies resembling asteroids. Comets are temporary in their activity, reminders that nothing lasts forever. Their journeys across the solar system are long, but their displays are fleeting, like fireworks on a cosmic scale. In the broader story of the solar system, comets link the inner and outer regions. They show how material from the edges can reach the heart, how the sun's gravity binds even the most distant fragments into orbits that eventually bring them back. They carry chemical signatures that inform us about the conditions of the early solar nebula. They may have played a role in delivering water and organics to Earth, seeding the ingredients that allowed life to begin. In that sense, comets are not only messengers of distance but of history and origin. When you think of the solar system's edge, it can feel abstract. Numbers like thousands of astronomical units or light years are hard to imagine. But when a comet blazes in the night sky, the edge becomes visible. It is as if the distant frontier has reached out and touched us, sending a small icy traveller across billions of kilometres to appear in our skies. Watching a comet is, in a way, watching the solar system reveal its vastness, condensed into a single moving point of light. As our exploration continues, comets will remain vital guides. Future missions may capture samples and return them to Earth, offering laboratory analysis of material unchanged for billions of years. Telescopes will discover more faint comets, expanding our understanding of the reservoirs they come from. And each time a bright comet appears, it will remind us again of the distances that shape the solar system and of the fragile, beautiful messengers that bridge them. Once you've passed through the region of Neptune and the Kuiper Belt, the sense of order begins to thin. The neat resonances that keep Pluto safe, the relatively stable orbits of classical Kuiper Belt objects, and the broad, icy band that rings the solar system give way to something less tidy. Beyond that point, many worlds follow paths that are stretched, tilted, and irregular. This is the realm astronomers call the scattered disk, and it's one of the most intriguing and mysterious regions of the solar system. The scattered disk is not a belt in the way the asteroid belt or Kuiper Belt is. It isn't a dense, evenly filled zone. Instead, it's a population of icy bodies whose orbits have been disturbed, often elongated into vast ellipses that take them far from the Sun. Their perihelia, or closest approaches, can still bring them near Neptune, but their aphelia, their farthest points, extend hundreds of astronomical units away. To an object in the scattered disk, the Sun is no longer the central dominant force it appears to us. Instead, it's a bright but distant star, one influence among many. How did these objects end up on such eccentric orbits? The leading explanation is that they were scattered outward by the giant planets, especially Neptune. In the early solar system, Neptune and the other giants did not necessarily occupy their current positions. Models of planetary migration suggest that as they moved through the protoplanetary disk, their gravity flung countless icy bodies outward. Some were ejected entirely, escaping into interstellar space. Others settled into the distant Oort Cloud, and some ended up in the scattered disk, on orbits that are stable over billions of years but far from regular. In a sense, the scattered disk is a fossil record of the solar system's restless youth, when planets and planetesimals jostled and rearranged themselves. The objects in the scattered disk are sometimes called wanderers because their orbits can be so extreme. Take Eris, for example. Discovered in 2005, it quickly gained fame for being larger than Pluto in mass, though slightly smaller in diameter. Eris orbits the Sun every 557 years, with a perihelion of about 38 AU and an aphelion of nearly 97 AU. Its elongated orbit takes it far beyond the Kuiper Belt, into territory that begins to blend into the outer reaches. The discovery of Eris was one of the catalysts for the reclassification of Pluto, forcing astronomers to recognise that Pluto was only one of many large worlds in this distant zone. Another striking example is Sedna, discovered in 2003. Sedna's orbit is even more extreme, with a perihelion of about 76 AU and an aphelion close to 1000 AU. Its orbital period is estimated at over 11,000 years. For most of that time, Sedna drifts in deep cold, so far from the Sun that it receives only the faintest light. Sedna's orbit is unusual enough that it cannot be explained simply by Neptune's influence. Astronomers suspect it was tugged into place by a passing star early in the solar system's history, or perhaps by an as yet undiscovered massive planet. Sedna is sometimes called a transitional object, one that bridges the scattered disk and the inner Oort Cloud. These extreme orbits raise questions that remain unresolved. Why do several scattered disk objects share similar orientations? Is it coincidence, or does it point to the presence of something unseen? This is where the idea of Planet 9 enters the conversation. Some researchers propose that a planet perhaps 10 times the mass of Earth, orbiting hundreds of AU away, could shepherd these distant objects into clustered orbits. The evidence is still debated. Some simulations suggest Planet 9 could explain the observations, while others argue the clustering might be a statistical illusion. Whether or not Planet 9 exists, the very fact that we are considering it shows how the scattered disk forces us to confront how little we know about the solar system's outskirts. The scattered disk is also important because it supplies many of the comets that enter the inner solar system. While the Kuiper Belt is thought to be the source of short-period comets, the scattered disk contributes intermediate and sometimes long-period ones. Gravitational nudges from Neptune can slowly shift their orbits until they cross into the inner regions, where sunlight awakens them into active comets. In this way, the scattered disk is not just a distant abstract region, but one that sends visitors to Earth's skies. Each time a comet passes, it is a reminder of the reservoir from which it came. Observing the scattered disk is difficult. These objects are incredibly faint, far smaller and more distant than planets. They reflect little sunlight and move so slowly against the background stars that it can take years to confirm their orbits. The discovery of each new scattered disk object requires patience, powerful telescopes, and careful tracking. Even then, we know only a fraction of what's out there. For every Sedna or Eris discovered, there may be dozens or hundreds more waiting invisible for now. The census is incomplete, and perhaps always will be, given the faintness of these bodies. Yet even the small sample we've identified tells us something profound. The scattered disk is evidence that the solar system's edge is not a neat boundary, but a gradient, a transition zone where orbits stretch out into the dark. It shows us that the influence of the giant planets extends far beyond their immediate orbits, shaping populations that lie hundreds of AU away. It also tells us that the solar system is not isolated. The idea that Sedna may have been influenced by a passing star suggests that the Sun's neighbourhood, billions of years ago, was a crowded place. The scattered disk preserves that history in its elongated orbits. From a broader perspective, the scattered disk challenges our sense of scale. The planets, even the giants, orbit in what now seems like a compact inner system. Neptune's distance of 30 AU once felt immense, but compared to Sedna's 1000 AU aphelion, it seems close. The scattered disk extends our awareness into realms where distances are no longer counted in decades of light travel time but in weeks or months. Light from the Sun takes over 13 hours to reach 100 AU, and nearly a week to reach Sedna at its farthest. These are distances where human intuition begins to falter, where even numbers start to lose their meaning. But despite their remoteness, scattered disk objects are not irrelevant. They are part of the solar system's story just as much as the planets and moons. They remind us that the Sun's influence stretches outward in ways that are not simple or symmetrical. They highlight how much we still have to learn, how incomplete our maps remain, and they invite us to consider that the solar system is not just the familiar planets, but a layered structure of populations, each with its own character. The scattered disk is also a place of possibility. If Planet 9 exists, it would belong to this region, a hidden giant shaping the orbits of its neighbours. If not, then the clustering we see may point to something else, perhaps a history of stellar encounters, or perhaps just the randomness of small number statistics. Either way, the scattered disk forces us to question our assumptions. It is not a finished story, but a mystery in progress, and as our telescopes grow more powerful, we will continue to find more of these wanderers. The upcoming Vera Rubin Observatory, with its wide-field survey capabilities, is expected to discover thousands of new trans-Neptunian objects, many of them in the scattered disk. Each new discovery will refine our picture, filling in details of the architecture. Perhaps one of them will reveal a pattern that confirms or disproves Planet 9. Perhaps one will show us an orbit so extreme that it reshapes our understanding once again. In the meantime, the scattered disk remains a frontier of uncertainty. Its members wander on paths that span centuries, millennia, or longer. They drift between the ordered world of the Kuiper Belt and the vast, unseen expanse of the Oort Cloud. They are the bridge between the known and the unknown, the messengers of a solar system that does not end cleanly but fades into interstellar space. Among all the distant worlds that have been discovered beyond Neptune, one stands out as especially peculiar. It is not the largest, nor the brightest, nor the most famous, and yet in many ways it is the most mysterious. This world is Sedna, a small reddish object whose orbit is so unusual that it has defied easy explanation since the day it was found. While other scattered disk objects stretch far, Sedna's path reaches into territory that lies between what we think of as the solar system and what we think of as interstellar space. It is a wanderer in a realm that few others seem to occupy, and its lonely path may hold clues to events from the solar system's earliest days. Sedna was discovered in 2003 by a team of astronomers led by Mike Brown. At first, it looked like just another distant, faint point of light moving slowly across the background stars. Careful tracking revealed something extraordinary. Its orbit was unlike anything seen before. At its closest, Sedna comes no nearer than about 76 astronomical units from the Sun. That's more than twice the distance of Pluto at its farthest. But its aphelion, its most distant point, stretches close to 1000 AU. That's about 33 times farther than Neptune, and so far that sunlight there is just a whisper, 10,000 times weaker than what we receive on Earth. Sedna takes over 11,000 years to complete a single orbit. In all of recorded human history, Sedna has never once returned to the same position in the sky. Every time we look at it, we are catching it at one instant in a journey that is longer than civilization itself. This orbit is not only extreme in scale, but strange in shape. Most scattered disk objects have perihelia closer to Neptune, allowing them to be perturbed by its gravity. Sedna, by contrast, never comes close enough. Its perihelion is too far away for Neptune to have placed it there. That's what makes it such a puzzle. How did Sedna end up on such an orbit, one that seems detached from the rest of the known solar system? One possibility is that Sedna was influenced by a passing star in the Sun's birth cluster. Stars are born in groups, condensed from giant molecular clouds, and in those early days the Sun would have had many stellar neighbours. If another star passed close enough, its gravity could have tugged objects like Sedna outward, pulling them onto elongated orbits without ejecting them entirely. Over billions of years, the Sun drifted away from its siblings, but Sedna's orbit remained as a fossil of that encounter. In this scenario, Sedna is a messenger from the solar system's infancy, carrying evidence of the Sun's crowded nursery. Another explanation invokes the possibility of a massive unseen planet in the distant solar system. The so-called Planet 9 hypothesis suggests that a super-Earth-sized planet, orbiting hundreds of AU from the Sun, could shepherd objects like Sedna into clustered, elongated orbits. Several distant objects seem to share orbital alignments that might point to such a planet's influence. If Planet 9 exists, it would be one of the most significant discoveries in modern astronomy, reshaping our picture of the solar system. Sedna's orbit is one of the strongest pieces of circumstantial evidence for its presence, yet so far no telescope has directly seen such a planet. The search continues, with powerful instruments scanning the skies for faint, slow-moving points of light. A third idea is that Sedna might have been captured from another star system entirely. In the crowded environment of the Sun's birth cluster, stars would have exchanged material. It is possible that Sedna began its life orbiting another star, only to be pulled into the Sun's gravity during a close encounter. If so, Sedna is not just a relic of our solar system's history, but a visitor from another. Its lonely orbit could mark it as an interstellar immigrant, now bound to our Sun but carrying a different origin. Regardless of how it arrived, Sedna is remarkable for what it represents. It shows that the outer solar system is not empty, but filled with objects that do not fit neatly into the categories we've created. Its orbit bridges the gap between the scattered disk and the inner Oort Cloud. It is too close to be considered part of the distant spherical cloud, yet too far to be explained by Neptune's influence. In that sense, Sedna is a transitional object, a signpost pointing toward regions we cannot yet see. Sedna itself is about 1,000 kilometers in diameter, making it large enough to be considered a dwarf planet. Its surface is one of the reddest in the solar system, a colour thought to come from tholins, complex organic molecules formed by the irradiation of methane and other ices. This reddish hue is also seen on other distant objects, suggesting similar processes shape them. Sedna's surface is cold, with temperatures averaging around minus 240 degrees Celsius. At such extremes, even nitrogen and methane are frozen solid. Because Sedna is so distant, observing it is a challenge. Even the largest telescopes can only gather limited light. No spacecraft has visited it, and none are currently planned. What we know comes from careful measurements of its brightness, its colour, and its motion. Each new observation adds a little more detail, but much remains unknown. Does Sedna have moons? Does it have an atmosphere, however thin? What internal processes shaped it? These questions await future exploration. The existence of Sedna has already expanded our imagination. Before its discovery, the solar system seemed to taper off at the Kuiper Belt and scattered disk. Sedna showed that there are objects far beyond, in a region we had not mapped. It suggested that the sun's reach extends in ways we did not anticipate. And it reminded us that the solar system's edges are not clean-cut but layered, blurred, and filled with surprises. From a human perspective, Sedna's orbit is almost incomprehensible. An orbit lasting 11,000 years means that entire civilizations rise and fall, while Sedna completes only a fraction of its journey. The last time Sedna was where it is now, humans were still living in the Stone Age. The next time it returns, the world will be unrecognisably different. Sedna's timescale dwarfs human history, connecting us to cosmic rhythms that stretch beyond anything familiar. It is a reminder that the solar system is not built on human times, but on vast cycles measured in millennia. When we consider Sedna's lonely path, it also highlights how incomplete our maps remain. If Sedna exists, surely there are others like it, perhaps many. We have only found it because its orbit currently brings it relatively close to the Sun, at least compared to its aphelion. When it drifts outward again, it will fade into invisibility. There may be dozens or hundreds of similar objects, hidden in the dark, waiting for the right alignment to be found. The Vera Rubin Observatory, once operational, is expected to reveal many more. With its wide surveys, it may uncover a whole population of Sedna-like worlds, each with its own story. Sedna reminds us that the solar system is not static. Its orbit may have been shaped by encounters with other stars, by hidden planets, or by capture events. Each possibility points to a dynamic past, a solar system that has interacted with its environment. The Sun is not isolated. It was born among siblings, moved through crowded stellar fields, and continues to drift through the galaxy, tugged by tides and encounters. Sedna is a fossil of those interactions, preserved in its path. Even in its loneliness, Sedna connects us to the larger universe. It shows that the solar system does not have a single boundary, but multiple overlapping zones. It demonstrates that the Sun's influence extends into places where light is weak, gravity is faint, and orbits are stretched across thousands of years. And it suggests that the line between the solar system and interstellar space is not sharp but gradual, filled with wanderers like itself. To think of Sedna is to think of patience. Its orbit is so slow that no human will ever see it complete a full cycle. Our instruments will track it, our descendants may map it more precisely, but the rhythm it follows belongs to cosmic time. It reminds us of how small we are, how brief our lifetimes are compared to the motions of even a single icy world at the edge of the Sun's domain. Yet in observing it, naming it, and wondering about it, we bring it into our own story, connecting our brief human moment to its immense, ancient path. As astronomers push their surveys deeper into the night sky, charting the faint and distant bodies far beyond Neptune, they began to notice something unusual. It wasn't a single discovery, like Pluto or Eris or Sedna, but a pattern. Several of these faraway objects seemed to share a strange alignment, as though their orbits were all being tugged in the same direction. In a system as vast and varied as ours, you would expect randomness. Orbits should tilt in many directions, spread out in a wide scatter. But these did not. They seemed to cluster, as though something unseen was exerting its influence from the shadows. That puzzle has led to one of the most intriguing and controversial ideas in modern planetary science, the possibility of a hidden giant planet, sometimes called Planet 9, lurking in the darkness of the outer solar system. The idea of unseen planets is not new. Neptune itself was discovered this way. In the mid-19th century, astronomers noticed that Uranus's orbit did not quite match predictions. Something was pulling on it. Careful calculations suggested the presence of another planet, farther out, and telescopes soon confirmed Neptune's existence. It was one of the great triumphs of predictive science. The idea that an invisible world could be revealed through its gravitational fingerprints has remained part of astronomy ever since. In the case of Planet 9, the same reasoning applies, but on a much grander scale. In 2016, two astronomers, Konstantin Batygin and Mike Brown, published a paper arguing that the clustering of several distant trans-Neptunian objects could be explained by the presence of a large, unseen planet. According to their calculations, this hypothetical planet would be about 10 times the mass of Earth, orbiting at a distance of perhaps 400 to 800 astronomical units. Its orbit would be highly elongated, taking thousands of years to complete a single revolution around the Sun. If such a planet exists, it would dwarf Pluto, Eris, and every other icy body beyond Neptune, instantly reclaiming a place among the major planets of the solar system. The evidence for Planet 9 comes from the orbits of objects like Sedna and several others discovered in recent years. These bodies, sometimes called extreme trans-Neptunian objects, have perihelia far beyond Neptune and aphelia stretching hundreds or thousands of AU. Their orbits are clustered in a way that suggests they are being shepherded by the gravity of a massive unseen companion. Without such a planet, the clustering seems statistically unlikely. With it, the pattern makes sense. The proposed Planet 9 would act as a distant shepherd, aligning orbits through its slow, steady pull. But evidence is not proof. Some astronomers argue that the clustering may not be as significant as it appears. The sample size is small, and observational bias could play a role. Surveys of the outer solar system are incomplete, and the regions we can scan most easily are not distributed evenly. It's possible that the apparent alignment is a coincidence, a product of where we've looked, rather than an actual pattern. Others suggest alternative explanations, such as the collective gravity of many smaller objects producing the same effect. Despite the debate, the search for Planet 9 continues. Large telescopes like Subaru in Hawaii have scanned wide swaths of sky, hunting for a faint, slow-moving point of light that could be the hidden world. So far, none has been found. If Planet 9 exists, it would be incredibly faint, reflecting only a tiny amount of sunlight across vast distances. Even with our best instruments, detecting it is a challenge. The search area is enormous, and the object would move so slowly that tracking it requires patience and persistence. Yet astronomers remain hopeful, refining their predictions and narrowing down where it might be hiding. If Planet 9 is real, its discovery would have profound implications. It would mean that the solar system contains a major planet we had overlooked until now, one orbiting far beyond the familiar 8. Its presence would help explain the structure of the outer solar system, the orbits of scattered disk objects, and perhaps even the tilt of the solar system's plane relative to the Sun's equator. It would reshape textbooks, expanding the solar system's known boundaries once again. The idea of Planet 9 also sparks the imagination. What would such a world be like? At 10 Earth masses, it would likely be a mini Neptune, with a thick atmosphere of hydrogen and helium surrounding a rocky core. Its surface, if it had one at all, would be buried beneath crushing pressures. Temperatures would be frigid, hundreds of degrees below zero, with only the faintest warmth from the sun. It would not be a place for life as we know it, but it would be a world in its own right, orbiting silently in the dark, unseen by human eyes for all of history until now. There are even bolder ideas. Some have speculated that Planet 9 could be a captured rogue planet, an object that once drifted through interstellar space before being caught by the Sun's gravity. Others wonder if it could be something even stranger, like a primordial black hole left over from the early universe, no larger than a grapefruit but with the mass of a planet. These are speculative ideas, far from confirmed, but they show the range of possibilities when dealing with such distant, hidden phenomena. Whether or not Planet 9 exists, the search itself has value. It forces astronomers to refine their models, to survey the sky more carefully, to push the limits of observation. It highlights how incomplete our map of the solar system remains. Even after centuries of discovery, we may still be missing a giant planet in our own neighbourhood. That possibility is humbling, reminding us that the cosmos always has more to reveal. The story of Planet 9 also ties into a larger theme. The solar system's edges are not well defined. Beyond Neptune, orbits become irregular. Populations are sparse. Forces overlap. The possibility of a hidden giant emphasizes that the outer solar system is not a simple, empty space, but a dynamic environment shaped by interactions we're only beginning to understand. For now, Planet 9 remains a hypothesis. No telescope has yet spotted it, no spacecraft has confirmed it. But the fingerprints it may have left in the orbits of distant objects keep the idea alive. Each new discovery of a far-flung icy body adds to the debate, either strengthening the case or challenging it. The answer may come in the next decade, as more powerful surveys scan the sky with unprecedented sensitivity. If Planet 9 is there, it will eventually be found. If it is not, then the clustering must be explained another way. Either outcome will teach us something important about how the solar system works. And so, when we look into the dark beyond Neptune, we do so with the knowledge that the story may not be complete. There may be a hidden giant moving slowly through the cold, shaping the orbits of smaller bodies, waiting to be revealed. Or there may not. Either way, the possibility itself has expanded our perspective, reminding us that the solar system is larger and stranger than we once thought. The search continues as astronomers scan the shadows, looking for a world that may or may not exist, but that already has changed the way we think about the sun's domain. When we talk about the limits of the solar system, it's easy to think only in terms of planets and orbits, solid worlds moving along predictable paths. But there's another boundary, one less tangible, that defines the sun's reach in a very different way. It's not a boundary of rocks or ice, but of particles and fields, of wind and pressure. This is the edge called the heliopause, and it's one of the most significant transitions in all of space exploration. The sun does not simply shine with light, it breathes. From its surface, streams of charged particles flow outward in every direction, a constant outpouring of plasma called the solar wind. These particles race away at hundreds of kilometers per second, filling the solar system with a tenuous but ever-present breeze. Near Earth, we feel its influence in the auroras that dance around the poles, in the disruptions it causes to satellites and radio signals, in the shaping of Earth's magnetic field. But the solar wind does not stop at Earth. It extends far beyond, filling a vast bubble that encompasses every planet, every asteroid, every icy body we call our own. That bubble is the heliosphere, and its outermost edge, where the solar wind finally yields to the interstellar medium, is the heliopause. You might imagine it as the place where the sun's influence ends and the galaxy begins, but the reality is more subtle. The sun's light can still be seen far beyond. Its gravity still reaches much farther. But in terms of plasma and magnetic fields, the heliopause marks a real shift. Inside, the solar wind dominates. Outside, the material between the stars pushes back. It's like standing at the shoreline where a river meets the sea. Two currents colliding, mixing, creating turbulence and change. The heliopause is that meeting place, a shifting frontier where the sun's personal environment gives way to the broader ocean of the galaxy. For a long time, the heliopause was only a theoretical concept. Scientists knew the solar wind must eventually slow, pile up, and be balanced by the pressure of the interstellar medium, but nobody knew how far away that would be. Estimates range from tens to hundreds of astronomical units. It wasn't until spacecraft actually travelled into the outer solar system that we began to measure it directly. Voyager 1, launched in 1977, became the first human-made object to cross the heliopause in 2012, more than 35 years after leaving Earth. At that time, it was about 121 AU from the Sun, or more than 11 billion miles away. The crossing was not like passing through a gate. There was no sudden wall. Instead, Voyager's instruments recorded gradual changes. The density of charged particles shifted. The direction of magnetic fields altered. Cosmic rays from interstellar space, previously deflected by the heliosphere, surged in number. These subtle clues told scientists that the spacecraft had entered a new environment. Voyager had left the solar wind behind and was now bathed in the plasma of the galaxy itself. Voyager 2, travelling on a different path, crossed the heliopause in 2018 at a distance of about 119 AU. Its instruments were still functioning well enough to provide more detailed measurements. It confirmed that the heliopause is not a fixed boundary, but a dynamic one. Its distance varies depending on solar activity, expanding and contracting with the Sun's 11-year cycle. In times of strong solar wind, the heliosphere swells outward. In quieter periods, it shrinks. The heliopause is not a rigid wall but a flexible membrane, breathing with the Sun's rhythm. Inside the heliosphere, the solar wind creates a protective bubble. It shields the planets from much of the cosmic radiation that pervades interstellar space. Without this shielding, Earth would be exposed to higher doses of energetic particles, which could affect the atmosphere, climate, and even the possibility of life. In this sense, the heliosphere is not just an abstract boundary, but a protective cloak, an invisible barrier that has shaped Earth's habitability for billions of years. The region just inside the heliopause is called the heliosheath, where the solar wind slows and becomes turbulent, buffeted by the pressure of the interstellar medium. Voyager's data showed that the transition is complex, with layers of plasma interacting in ways we are only beginning to understand. Some models suggest that magnetic reconnection events occur here, where magnetic field lines snap and reform, releasing energy. Others propose that the heliopause is porous, with particles leaking across in both directions. Far from being a clean line, it is a frontier of mixing and change. Beyond the heliopause, the interstellar medium itself is not empty. It contains sparse atoms, dust grains, and magnetic fields. It is the material between stars, shaped by supernova, stellar winds, and galactic tides. To cross the heliopause is to leave the Sun's private domain and enter the shared environment of the galaxy. Voyager's instruments, though limited, have given us our first direct taste of that realm. They recorded plasma waves, measured cosmic ray intensities, and mapped the density of interstellar particles. For the first time, humanity had a foothold, however small, in true interstellar space. The heliopause also raises profound questions about the solar system's place in the galaxy. How typical is our heliosphere? Do other stars create similar bubbles? Observation suggests that every star with a strong wind should have a heliosphere of its own, each one a protective cocoon shielding planets from cosmic rays. Some may be smaller, others larger, depending on the star's activity and its environment. Our own heliosphere may even leave traces visible from outside, a kind of bow shock where it ploughs through the interstellar medium. By studying the heliopause, we not only learn about the Sun, but about stars in general. For spacecraft, crossing the heliopause is a milestone, but not an end. Voyager 1 and 2 are still travelling outward, their radio signals growing fainter with each passing year. They carry with them not only instruments, but messages, the famous golden records, engraved with sounds and images of Earth, sent as a greeting to any future beings who might find them. Long after their instruments fail, they will continue drifting through interstellar space, silent emissaries of humanity. The fact that they have crossed the heliopause means that they are no longer only solar system explorers, but interstellar travellers, however small and slow. The heliopause is also a reminder of scale. At 120 AU, it is far beyond any human journey so far, yet it is only a fraction of the solar system's extent. The Oort Cloud, if it exists as predicted, extends tens of thousands of AU. That means the heliopause is just the first step into the broader frontier. It is like leaving the shore but still being in coastal waters, with the true open ocean stretching far beyond. Crossing it is significant, but it is only the beginning of interstellar exploration. One of the most fascinating aspects of the heliopause is how it embodies the idea of invisible borders. Unlike the orbit of a planet, which can be drawn as a neat ellipse, the heliopause has no simple geometry. It shifts, warps, and responds to external pressures. It is shaped not only by the Sun but by the galaxy around it. To define it is to accept that boundaries in space are not clean edges but complex transitions. The heliopause is the solar system's frontier not because it is absolute, but because it is the place where the Sun's influence begins to give way. For future missions, the heliopause offers both a challenge and an opportunity. Designing spacecraft to survive and measure conditions there requires durability and patience. Signals take over 16 hours to travel from Voyager 1 to Earth, and each year that delay grows. Power sources must last for decades. Instruments must be reliable over timescales longer than most technological lifespans. Yet the payoff is immense. Direct exploration of the boundary between solar and interstellar space, a frontier that until recently was only imagined. When we think of the solar system's end, the heliopause offers one of the most concrete answers. It is a physical boundary, measurable, crossed by spacecraft, defined by changes in environment. It is not the end of the Sun's gravity or light, but it is the end of its wind. It is where our star's personal bubble ceases and the galaxy begins, and as we continue to send probes outward, it is the place where we first step into that larger stage, where the familiar gives way to the unknown. The Sun is often described as a shining ball of fire, but that image, though poetic, misses the reality of what a star truly is. The Sun is a sphere of plasma, a vast nuclear engine whose surface churns with magnetic storms, flares, and eruptions. It does not simply give off light, it sends out a wind, a continuous outflow of charged particles that streams across space at hundreds of kilometers per second. This flow is the solar wind, and over billions of years, it has inflated a bubble around the Sun, a vast invisible structure that contains every planet, every asteroid, every comet that orbits our star. That bubble is the heliosphere, and to understand it is to understand one of the most remarkable features of our solar system. The solar wind begins in the Sun's outer atmosphere, the corona, where temperatures reach millions of degrees. At such high energies, electrons and protons cannot remain bound to atoms. They move freely, colliding and accelerating, carried outward by the pressure of heat and magnetic fields. These particles escape the Sun's gravity, rushing outward into space. Near Earth, the solar wind is usually travelling at speeds of 400 to 800 kilometers per second. Though tenuous, just a few particles per cubic centimeter, it carries enough energy to shape magnetic fields, create auroras, and even erode planetary atmospheres over geological timescales. The solar wind does not flow uniformly, not flow. It changes with the Sun's activity, strengthening during solar maximum when sunspots and flares are frequent, and weakening during solar minimum. Coronal mass ejections can send powerful bursts of plasma that travel outward as shockwaves, disturbing planets and spacecraft along the way. But beyond the inner solar system, these variations average out, and the solar wind becomes a steady outward flow, filling the heliosphere with plasma and magnetic fields. The heliosphere is immense, extending more than 100 astronomical units from the Sun in all directions. Inside, the solar wind dominates, pushing back against the interstellar medium. Outside, the material between the stars, the interstellar plasma, dust and magnetic fields, exerts its own pressure. Where the two meet, the solar wind slows, piles up and eventually stops. That boundary, as we've seen, is the heliopause, but the heliosphere itself, the bubble inflated by the solar wind, is a structure that stretches across a volume so large that light takes more than a day to cross it. To imagine the heliosphere, think of a boat moving through water. As it moves, it creates a bull wave ahead and a wake behind. The Sun moves through the galaxy in a similar way, carrying its bubble of solar wind with it. For a long time, scientists thought the heliosphere might resemble a comet, with a rounded front and a long trailing tail. More recent observations suggest it may be more complex, perhaps shaped like a croissant with two extended lobes, sculpted by interactions between magnetic fields. Whatever its shape, it is vast beyond comprehension, a structure created by our star's constant breath. Inside the heliosphere, the solar wind plays many roles. It shapes planetary magnetospheres, carving bow shocks and tails around worlds like Earth, Jupiter, and Saturn. It drives auroras on Earth and other planets, as charged particles funnel along magnetic field lines and collide with atmospheres, creating glowing curtains of light. It transports magnetic energy outward, connecting the Sun to its planets in ways both visible and invisible. Without the solar wind, the solar system would be quieter, darker, and less dynamic. The heliosphere also acts as a shield. Cosmic rays, high-energy particles from distant supernovae and other astrophysical events, constantly bombard the galaxy. The solar wind's magnetic field deflects many of these, reducing the radiation that reaches the inner planets. This shielding is not perfect. Cosmic rays still penetrate, affecting technology and perhaps even life's mutation rates, but it is significant. The heliosphere is like a cocoon, protecting Earth and its neighbours from the harshest interstellar radiation. Changes in the heliosphere over time may even have influenced Earth's climate and biological history. The size of the heliosphere is not constant. It expands and contracts with the solar cycle, and it may change over longer timescales as the Sun moves through regions of different interstellar density. If the Sun passes through a denser cloud of interstellar gas, the heliosphere could shrink dramatically, exposing the planets to higher levels of cosmic rays. Some scientists speculate that such passages may have occurred in the past, potentially affecting Earth's climate and even mass extinctions. The heliosphere is not just a bubble around the Sun. It is a living structure, shaped both from within by solar activity and from without by the galaxy. The only direct measurements of the heliosphere's edge have come from Voyager 1 and Voyager 2, but other spacecraft have helped map its interior. Instruments on missions like Ulysses, Pioneer, and IBEX, the Interstellar Boundary Explorer, have traced the solar wind's flow, its variations, and its interactions with magnetic fields. IBEX in particular has created maps of energetic neutral atoms, particles created when solar wind protons capture electrons from interstellar atoms. These maps provide a global picture of the heliosphere, showing its boundaries and asymmetries. More recently, NASA's Interstellar Mapping and Acceleration Probe, IMAP, planned for launch in the 2020s, aims to expand this view, giving us the most detailed understanding yet of the solar wind's great bubble. From a human perspective, the heliosphere may seem abstract. We don't feel the solar wind on our skin, we don't see the heliopause with our eyes, and yet its presence affects us every day. It shapes the conditions of space weather, influences the safety of astronauts, protects Earth from radiation, and marks the true frontier between the Sun's domain and the galaxy beyond. Every spacecraft, every signal, every journey outward must pass through it. To understand the solar wind's bubble is to understand the environment we live in, not just as inhabitants of Earth, but as citizens of a solar system enclosed within an invisible shield. The heliosphere also ties into the larger theme of boundaries. Just as the orbits of planets give us one way to define the solar system's edge, and the Oort Cloud offers another, the heliosphere provides a third. It is the bubble of influence carved out by the Sun's wind, distinct from gravity or light. If you define the solar system by where the Sun's particles dominate, then the heliopause is the edge, and the heliosphere is its domain. It is one of several overlapping answers to the question of how far the solar system goes. What makes the heliosphere so fascinating is that it's both fragile and immense. It is created by something as tenuous as a stream of particles so thin it would be a vacuum by earthly standards, yet it extends trillions of kilometers. It is invisible, yet spacecraft can measure its presence. It is dynamic, changing with cycles of years, centuries, and eons, and it is essential, shaping the environment of every planet within. When we imagine the solar system, we often picture planets orbiting in empty space. But in reality, they orbit within this bubble of solar wind, connected to the Sun not only by gravity and light, but by a constant flow of particles. The heliosphere is the invisible stage on which the solar system's drama unfolds. To recognize it is to see the solar system not just as a collection of bodies, but as a dynamic system shaped by its star's breath. In the late 1970s, when disco still filled dance halls, when personal computers were still a novelty, and when the idea of leaving the solar system seemed more like science fiction than science, 2 spacecraft were launched that would eventually change our sense of place forever. They were called Voyager 1 and Voyager 2, twin probes built with 1970s technology, powered by radioisotope thermoelectric generators, guided by computers that were primitive even by the standards of the time, yet their missions would outlast entire generations of machines and expectations. They were meant to tour the giant planets, to send back images and data of Jupiter, Saturn, Uranus, and Neptune. But their journeys did not end there. They kept going, crossing distances no human-made object had ever reached. They became the first emissaries of Earth to step beyond the solar wind's reach. They became our far-flung storytellers, carrying human voices into interstellar space. Voyager 2 launched first in August of 1977, followed by Voyager 1 a few weeks later in September. Their timing was deliberate. The late 1970s offered a rare alignment of the outer planets, a once-in-176-year configuration that allowed a spacecraft to slingshot from one giant planet to the next using gravity assists. This so-called grand tour meant that with a single launch, a probe could visit multiple worlds, each flyby boosting it onward to the next. Voyager 2 would go on to visit all 4 giants, Jupiter, Saturn, Uranus, and Neptune, the only spacecraft ever to do so. Voyager 1 would focus on Jupiter and Saturn, taking a faster trajectory that eventually propelled it toward interstellar space. The images they returned transformed our understanding of the solar system. At Jupiter, Voyager revealed storms and cloud bands in unprecedented detail, showing the Great Red Spot as a swirling vortex larger than Earth, with smaller storms scattered across the planet's face. It showed lightning in Jupiter's atmosphere, volcanic activity on its moon Io, the first time active volcanoes were seen beyond Earth, and icy fractures on Europa, hinting at a subsurface ocean. Ganymede and Callisto, once thought to be inert, were revealed as worlds with complex surfaces. Each discovery rewrote textbooks, showing that the solar system was far more dynamic than imagined. At Saturn, Voyager revealed the intricacies of the ring system, countless thin ringlets braided and twisted, shaped by the gravity of shepherd moons. It discovered new moons, observed the hazy atmosphere of Titan, and captured the hexagonal jet stream at Saturn's North Pole. Voyager's images of Saturn's moons revealed diverse landscapes, Mimas with its giant crater, Enceladus with hints of resurfacing, Iapetus with its stark two-tone colouring. These flybys did not just confirm theories, they generated entirely new questions, many of which remain today. Voyager 2's journey continued farther. In 1986, it flew past Uranus, revealing a planet that appeared bland in visible light, but whose moons were full of surprises. Miranda, in particular, displayed a patchwork of terrains, cliffs, and faults, as though stitched together from fragments. 3 years later, Voyager 2 reached Neptune, showing its deep blue atmosphere with high-speed winds and dark storms, including the Great Dark Spot. Triton, Neptune's largest moon, revealed geysers of nitrogen erupting from beneath its icy surface. With that encounter, Voyager 2 completed the Grand Tour, the first and only spacecraft to visit all 4 outer planets. After those planetary encounters, the Voyagers kept travelling outward. Their missions extended again and again as long as their instruments continued to function. They began the Voyager interstellar mission, tasked with studying the outer heliosphere and beyond. They measured the solar wind as it weakened with distance, the cosmic rays that grew stronger as shielding faded, and the magnetic fields at the boundary between solar and interstellar space. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. These crossings were subtle, recorded not as a dramatic shift but as gradual changes in plasma density, particle counts, and magnetic fields. But they marked a milestone. For the first time, our machines had left the bubble of the solar wind and entered the environment between the stars. Humanity had extended its reach, not in person, but in proxy, through 2 aging spacecraft still faithfully transmitting faint signals across billions of miles. Communication with the Voyagers requires the Deep Space Network, a system of large radio antennas located in California, Spain, and Australia. Even with these massive dishes, the signals are incredibly faint, arriving at Earth with a power less than that of a household light bulb spread across the vastness of space. It takes more than 20 hours for a signal to travel from Voyager 1 to Earth, and the delay increases with every passing day. The fact that we can still hear them at all, more than 4 decades after launch, is a testament to both engineering and persistence. The Voyagers are not just scientific probes. Each carries a golden record, a copper phonograph disc plated in gold, designed as a time capsule and a greeting to any beings who might one day encounter the spacecraft. The records contain sounds of Earth, greetings in 55 languages, music from cultures around the world, recordings of natural sounds like waves, thunder, birdsong, and laughter. They include images encoded in analog form, depicting landscapes, human life, animals, and scientific diagrams. Engraved on the covers are instructions for how to play them, and a map showing the position of the Sun relative to nearby pulsars. It is a message in a bottle cast into the cosmic ocean, unlikely ever to be found but meaningful in its intent. It symbolizes a desire not only to explore but to connect, to declare our presence in the galaxy. The golden records embody a paradox. On one hand, the chance that another civilization will ever find and decipher them is infinitesimal. Space is vast, the Voyagers are tiny, and their paths are random relative to the stars. On the other hand, the act of sending them carries profound meaning. It shows that in the moment of reaching outward, humanity chose not just to observe but to share. We didn't only send instruments to measure plasma or magnetism, we also sent voices, art, and greetings. We acknowledged that exploration is not just about knowledge but about identity, about telling others who we are. As the Voyagers drift farther, their instruments gradually shut down, one by one, as power dwindles. Their plutonium power sources decay steadily, producing less electricity each year. Engineers at NASA ration power carefully, turning off heaters and instruments to extend their lifespans. Eventually, sometime in the coming decades, they will fall silent. They will continue to drift, their golden records intact, but without a voice to send back. They will become relics of a particular moment in human history, silent ambassadors carrying a fragment of our world into eternity. Even in their silence, they will continue to move. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a small star called Gliese 445. Voyager 2 will pass within a few light-years of another star in about 300,000 years. By then, human civilization will be unimaginably different, or perhaps gone altogether. The Voyagers will continue regardless, their trajectories unaffected, their records still intact, long outlasting the cultures that built them. The legacy of the Voyagers is not only scientific but cultural. They showed us the outer planets in detail for the first time. They gave us images of moons and rings and storms that were far beyond anything telescopes could capture. They proved that small probes, carefully built and patiently guided, could last for decades and cross billions of miles. And they carried with them a message that blended science with hope, a gesture that said we are part of the cosmos and we are reaching out. In a way, the Voyagers are mirrors. They reflect both our technological abilities and our aspirations. They show what humanity can achieve when it looks outward with curiosity. They remind us that even fragile machines, launched on rockets designed before the internet existed, can travel farther than anyone ever expected. They remind us that exploration is a long game, measured not in years but in generations. When we think about the solar system's edge, the Voyagers give us a tangible point of contact. They are out there now, still moving, still transmitting, still crossing thresholds. They show us that the heliosphere has a real boundary, that interstellar space is not just a concept but a place that can be reached. And they carry our story with them, a story encoded in metal and grooves drifting endlessly outward. The question of how far the solar system goes is partly answered by the Voyagers. They have shown us the bubble of the solar wind, the heliopause, and the transition to interstellar space. They will never reach the Oort Cloud in their working lifetimes, but their paths lead toward it, even if silently. They remind us that the solar system is not an isolated stage, but part of a larger galaxy, connected by gravity, radiation, and motion. And as they travel, we listen. Every faint signal is a heartbeat, a reminder that our farthest storytellers are still speaking. Every data packet carries not just measurements, but meaning. The meaning of persistence, of endurance, of curiosity stretched across billions of miles. The Voyagers are not only machines, they are extensions of human imagination, still unfolding their journey, still narrating the story of leaving home. When people picture the solar system, they usually imagine a flattened disk, the sun in the centre, the planets circling on nearly the same plane, and perhaps a scattering of icy bodies just beyond. But if we stretch our minds farther, past Neptune, past the Kuiper Belt, past the scattered disk and even the paths of strange wanderers like Sedna, we reach a region that does not look like a disk at all. Instead, it surrounds the solar system in every direction, a vast spherical shell of icy bodies that stretches halfway to the nearest stars. This is the Oort Cloud, one of the most mysterious and remote structures associated with our Sun, and though no telescope has ever seen it directly, its existence is supported by compelling evidence. It is the ghostly shell of the solar system, unseen yet deeply significant. The idea of the Oort Cloud was first proposed in 1950 by the Dutch astronomer Jan Oort. He was studying the orbits of comets, especially long-period comets that take thousands or even millions of years to return. These comets arrive from all directions, not just along the plane of the planets. Their distribution suggested they come from a reservoir that is spherical, surrounding the Sun on all sides. Oort reasoned that such a reservoir must exist, holding perhaps trillions of icy bodies, each a leftover from the solar system's formation. When one of these bodies is nudged inward by the gravity of a passing star or galactic tide, it becomes a long-period comet, diving into the inner solar system for a brief, spectacular display before retreating again into the deep freeze. The scale of the Oort Cloud is almost impossible to grasp. Estimates place its inner edge at around 2,000 astronomical units, far beyond the Kuiper Belt. Its outer edge may reach 50,000 AU, or even 100,000 AU, nearly 2 light-years from the Sun. That distance is comparable to the halfway point between our Sun and Proxima Centauri, the nearest star. In other words, the Oort Cloud is not just a boundary of the solar system, it is a bridge, stretching so far that it overlaps with the gravitational spheres of influence of neighbouring stars. If you define the solar system by where the Sun's gravity can still hold objects, the Oort Cloud is the true extent. Unlike the planets or the Kuiper Belt, the Oort Cloud cannot be seen directly. Its members are too small, too dark, and too far away. Even the largest telescopes cannot detect them. Instead, we infer their existence from the comets they send our way. Long-period comets arrive from every direction in the sky, not just from the disk of the planets. Their orbits suggest they come from a spherical distribution. The numbers also make sense. To account for the steady arrival of long-period comets over billions of years, the Oort Cloud must contain an enormous population, perhaps 1 trillion or more icy bodies larger than a kilometre. The Oort Cloud is thought to have formed early in the solar system's history. As the giant planets migrated, they scattered countless icy planetesimals outward. Some were ejected entirely, lost to interstellar space. Others settled into distant orbits, held loosely by the sun's gravity. Encounters with passing stars and galactic tides gradually spread these orbits into a spherical distribution. Over time, what began as a disk of icy fragments became a vast shell. The Oort Cloud is thus a fossil of planetary formation, preserving the remnants of the early solar system in a frozen halo. There are likely 2 components to the Oort Cloud. The inner Oort Cloud, also called the Hills Cloud, which extends from about 2,000 to 20,000 AU, and the outer Oort Cloud stretching to 50,000 AU or more. The inner cloud is more tightly bound to the Sun, while the outer cloud is so loosely bound that passing stars or galactic tides can easily perturb it. The outer cloud is the source of most long-period comets, while the inner cloud may act as a reservoir, slowly feeding the outer population over time. Together they form a layered shell that has persisted for billions of years. Because it is so distant, the Oort Cloud is vulnerable to influences from outside the solar system. When a star passes within a few light years, its gravity can stir the outer Oort Cloud, sending a shower of comets inward. The galaxy's tidal forces also act over long timescales, gently tugging on the distant orbits. These perturbations occasionally send icy bodies hurtling toward the Sun, where they become comets visible from Earth. Some scientists have even suggested that periodic comet showers from the Oort Cloud could be linked to mass extinctions in Earth's history, though the evidence is debated. Whether or not such links exist, the Oort Cloud ensures that the solar system is not isolated but connected, constantly influenced by its galactic environment. The comets that come from the Oort Cloud are time travellers. They spend most of their lives in deep freeze, orbiting in darkness where the Sun is just another star. Then, nudged by gravity, they fall inward on a journey that can take millions of years. For a brief time near the Sun, they flare into brightness, growing tails of gas and dust, visible to humans who gaze up from Earth. Then, unless they are destroyed or ejected, they retreat once more into the outer reaches, perhaps never to return in human timescales. Each comet we see in the sky is a messenger from the Oort Cloud, carrying material preserved since the solar system's birth. The existence of the Oort Cloud also changes how we think about the solar system's boundaries. If you define the solar system by the orbits of planets, it ends with Neptune. If you define it by the Kuiper Belt, it ends around 50 AU. If you define it by the heliosphere, it ends around 120 AU. But if you define it by the reach of the Sun's gravity, then the solar system extends to the outer edge of the Oort Cloud, nearly 2 light-years away. By that measure, the solar system is vast beyond imagination, encompassing a space so large that the planets themselves occupy only a tiny fraction of it. Though unseen, the Oort Cloud is central to our understanding of the solar system. It explains the origin of long-period comets. It preserves the debris of planetary formation. It connects the solar system to its galactic environment. And it challenges us to think in scales that stretch far beyond the familiar. Future missions may one day probe the Oort Cloud directly, though the distances are daunting. At tens of thousands of AU, even the fastest spacecraft would take thousands of years to reach it. For now, our knowledge must come indirectly, from comets and models and inference. But even without direct observation, the Oort Cloud stands as one of the most powerful ideas in planetary science. an unseen structure that defines the true extent of the Sun's domain. When we imagine the Oort Cloud, we imagine not a dense swarm but a vast emptiness filled with scattered icy bodies, each one separated by millions of kilometers from the next. They are so far apart that even if you stood on one, you would not see another with the naked eye. It is a realm of solitude where time stretches endlessly, where orbits take millions of years, where silence reigns. And yet, it is connected to us, sending occasional visitors that light our skies and remind us of its presence. The Oort Cloud is ghostly because it is unseen, but also because it is transitional. It is the place where the Sun's influence fades into the galaxy, where the boundary between solar and interstellar becomes blurred. It is the solar system's shadow stretching across space, invisible yet real. To contemplate it is to realize that our home is larger and stranger than we ever thought, and that even now, after centuries of discovery, most of it remains unexplored. When we think about what binds the solar system together, the answer is always gravity. From the planets to the tiniest grains of dust, from comets arcing in toward the Sun to icy bodies on the very edges of the Oort Cloud, everything that belongs to the solar system is there because the Sun's gravity still holds it. The pull of the Sun is weak at great distances, but it never fully disappears. Even 2 light-years away, in the outermost stretches of the Oort Cloud, the Sun's gravity is still at work, subtle but real, maintaining a fragile hold on bodies that orbit once in millions of years. To understand where the solar system truly ends, we must understand how far that grip extends and where it begins to lose its dominance to the galaxy around us. Gravity is universal. Every mass attracts every other mass, no matter how far apart. But the strength of that pull decreases with the square of the distance. At Earth's orbit, the Sun's pull is strong enough to hold a planet 100 times the mass of Earth itself. At Neptune's orbit, the pull is weaker, but still sufficient to guide a giant planet nearly 20 times the size of Earth. By the time you reach the inner Oort Cloud, the Sun's pull is almost delicate, competing with the subtle tug of passing stars and the diffuse pull of the Milky Way itself. That competition sets the ultimate boundary of the solar system, the point where the Sun no longer dominates, where other forces claim control. Astronomers call this boundary the Hill sphere of the Sun. It is the region of space where the Sun's gravity is stronger than the tidal forces of the galaxy. Within the Hill sphere, objects can orbit the Sun. Beyond it, they drift away, captured instead by the gravity of the galaxy or neighbouring stars. For the Sun, the Hill sphere is vast, extending perhaps 2 or 3 light-years in radius. That's far beyond even the outer Oort Cloud. It means that in principle, the Sun could hold onto objects almost halfway to the nearest stars. But in practice, the outermost parts of this sphere are fragile. A passing star, even one many trillions of kilometers away, can disturb objects near the edge. The Oort Cloud is shaped by these interactions, stretched and eroded over billions of years. This tug-of-war between the Sun and the galaxy has been happening since the beginning. When the solar system first formed, the Sun was not alone. It was born in a cluster of stars, likely a few hundred siblings packed into a dense region of space. In that environment, close stellar encounters would have been common, tugging at the Sun's outer regions, stripping some material away and leaving behind a scattered population. As the cluster dispersed and the Sun moved into the quieter arms of the Milky Way, encounters became rarer but not non-existent. Even now, stars occasionally pass within a light-year or two, and each passage stirs the outermost parts of the Oort Cloud. These encounters remind us that the Sun's gravity is powerful but not absolute. It holds tightly near the centre, but at the edges its grip is contested. The way gravity defines the solar system is not only about distance, but about balance. Consider a comet deep in the Oort Cloud. Its orbit is determined by the Sun, but it is elongated, stretched and sensitive to small perturbations. If a passing star exerts just enough pull, the comet's path changes. It may be nudged inward, falling toward the Sun, and eventually flaring into brightness as a long-period comet. or it may be nudged outward. Its orbit widened until the Sun can no longer hold it, and it drifts into interstellar space. The balance is delicate. Gravity holds on tight, but only up to a point. Closer in, the Sun's gravity is not only dominant but decisive. It sculpts the orbits of planets into neat ellipses, maintains resonances that stabilize Pluto and other Kuiper Belt objects, and defines the rhythms of seasons and years on Earth. Without the Sun's grip, the planets would scatter, drifting into the void. Gravity is the framework, the invisible architecture that keeps the solar system coherent. Its tight hold is why the planets can orbit for billions of years in relative stability, why the asteroid belt remains in place, and why comets return again and again along predictable paths. At the same time, gravity is also the reason why the solar system has such structure. The asteroid belt exists where Jupiter's gravity prevented a planet from forming, scattering material into smaller fragments. The Kuiper Belt exists where Neptune's gravity shepherded icy bodies into resonances. The scattered disk is filled with objects flung outward by gravitational encounters with the giants. Everywhere we look, we see the Sun's pull at work, not just holding objects in place, but sculpting them into patterns and populations. The solar system is not random. It is the product of gravity's persistent and precise shaping. When we think of gravity holding on tight, it's also worth remembering that the Sun is not the only source of it. Every planet, every moon, every asteroid exerts its own pull. Moons orbit planets because planetary gravity dominates over the suns at those distances. Rings form because small particles are held in delicate balance between planetary tides and orbital motion. Even tiny asteroids can have their own miniature systems, with small moonlets orbiting them. Gravity scales, from the vast pull of the Sun to the tiniest tug of a rock only a few kilometers across. The hierarchy of these forces is what makes the solar system layered and interconnected. The hold of gravity also sets the timescales of motion. A planet close to the Sun orbits quickly, bound tightly by gravity. Mercury completes its year in just 88 Earth days. Farther out, Neptune takes 165 years. In the Oort Cloud, orbits stretch into millions of years. The weaker the grip, the longer the orbit. This stretching of time with distance is another way of seeing how gravity defines the solar system. It not only determines where objects are, but how quickly they move, how long their journeys take, how slow or fast their rhythms are. One of the most striking ways to appreciate the Sun's gravitational hold is to consider escape velocity, the speed required to break free from its pull entirely. Near Earth, that velocity is about 42 kilometers per second relative to the Sun. For Voyager 1, moving at about 17 kilometers per second, the Sun's gravity still has a claim, but not enough to pull it back. Voyager is on an escape trajectory, never to return, and yet, even now, it is still under the Sun's influence in the sense that its path is curved relative to the galaxy. Escape is not abrupt. It is gradual, a matter of never turning back. For the countless icy bodies in the Oort Cloud, most never achieve that velocity. They remain bound, however loosely, their fates tied to the Sun across aeons. There is also a poetic irony in how gravity both holds and releases. It binds the planets into orbits so stable that civilizations can build calendars and predict eclipses thousands of years in advance. But at the edges it allows fragility. A passing star, a galactic tide, or even the cumulative nudges of giant planets can free an object, sending it away forever. The solar system is not a sealed box. It leaks, slowly but steadily, exchanging material with the galaxy. Gravity holds on tight, but not infinitely tight. The Hill sphere, the mathematical boundary where the Sun's pull dominates, is an enormous region, but it is not absolute in practice. The reality is more dynamic. The Milky Way's gravity pulls on everything. Stars orbit the galactic center, carrying their systems with them. As the Sun orbits the galaxy once every 230 million years, It passes through different regions, denser or thinner, with clouds of gas, with spiral arms, with nearby stars. Each passage exerts its influence, shaking the Oort Cloud, shifting orbits, occasionally sending cascades of comets inward. The Sun's gravity is strong, but the galaxy's is stronger, and at the edges the balance tips back and forth. When we ask where gravity holds on tight, the answer depends on how far we're willing to follow. Near the Sun, the hold is absolute. The planets will not wander away on their own. In the Kuiper Belt, the hold is still secure, though orbits are stretched. In the scattered disk, the hold is tenuous, challenged by encounters and resonances. In the Oort Cloud, the hold is fragile, always under contest. Beyond that, the Sun's gravity fades into the background, overtaken by the collective pull of the galaxy. The story of the solar system is the story of this gradient, from the tight grip near the centre to the loose grasp at the edges. And yet, even in the vastness, gravity never truly lets go. Every object that was once bound to the Sun still feels its pull, however small. Even stars influence one another faintly across light years. Gravity is infinite in reach, though not in dominance. It ties everything together in one interconnected web. To speak of where gravity holds on tight is really to speak of where its influence is strongest, where it shapes structure and motion in ways we can clearly trace. But even beyond, its whisper continues. In contemplating the Sun's gravitational hold, we see the solar system not as a set of isolated parts, but as a continuous field of influence, fading with distance but never ending. It is a reminder that boundaries are not sharp, but gradients. The solar system does not stop abruptly. It tapers, thinning into the galaxy, held loosely at first, then barely at all. And in that tapering, we see how the Sun connects to the Milky Way, how our local system is part of something larger. Gravity holds us, but it also links us outward, tying the small to the vast, the local to the galactic. It is easy to imagine the Sun's influence as absolute. After all, we live within its reach every day. Its light warms our world, its gravity holds the planets in their orbits, its magnetic fields shape the flow of space around us. For life on Earth, the Sun feels like the ultimate authority. But as we move farther away, we are faced with the question of where that authority begins to weaken. How far does it go? At what point does the Sun's power fade into the background, replaced by the larger forces of the galaxy? This is not a simple question, because the Sun influences the solar system in many different ways. Each kind of influence fades at a different distance. The most obvious influence is light. At Earth, sunlight is abundant, pouring down with an intensity that sustains life, drives climate, and fuels photosynthesis. By the time you reach Jupiter, sunlight is already 25 times weaker. At Neptune, it is nearly 1,000 times weaker. Beyond that, in the Kuiper Belt, the Sun is still the brightest object, but no longer overwhelming. At the distance of the Oort Cloud, sunlight is so faint it resembles starlight. Imagine standing on an icy body there. The Sun would appear as just another bright star in the sky, only slightly larger than the others. Its warmth would be negligible, its light barely enough to cast a shadow. In terms of illumination, the Sun's influence fades to almost nothing long before you reach the solar system's true edge. Gravity is different. Unlike light, it does not fade to zero with distance. It weakens, but it never vanishes. Every object in the universe pulls on every other, no matter how far apart. The Sun's gravity binds the planets, the asteroids, the comets, and even the distant Oort Cloud. But while its reach is infinite, its dominance is not. At some point, the gravitational pull of nearby stars and the overall gravity of the Milky Way become stronger influences on the motion of objects than the Sun's. Astronomers call the outer limit of the Sun's gravitational dominance the Hill sphere, and for the Sun, that extends perhaps 2 or 3 light years. By that measure, the solar system stretches much farther than the planets, farther even than the Oort Cloud. But beyond that, the Sun's pull fades into insignificance compared to the galaxy. Objects drifting beyond that point are no longer bound. They belong to the Milky Way as a whole, not to the Sun. There is also the influence of the solar wind, the outflow of charged particles from the Sun. This flow inflates the heliosphere, a bubble that shields the planets from interstellar cosmic rays. The heliosphere ends at the heliopause, where the pressure of the solar wind is balanced by the interstellar medium. Voyager 1 and Voyager 2 crossed that boundary at around 120 AU. Beyond that, the Sun's plasma influence fades. It no longer dominates the particle environment. The heliosphere is therefore one kind of edge, a place where one aspect of the Sun's influence ends. But it is only one. Then there are magnetic fields. The Sun's magnetic influence stretches far, carried outward by the solar wind. Inside the heliosphere, its magnetic field lines twist and spiral, shaping interactions with planets and guiding charged particles. Beyond the heliopause, the interstellar magnetic field takes over. Here again, there is no single line but a transition, a place where the Sun's field yields to that of the galaxy. In terms of magnetism, the Sun's influence fades at about the same place as the solar wind, hundreds of times the Earth-Sun distance, but still tiny compared to the solar system's full gravitational reach. Another way to think about influence is in terms of habitability. For Earth, the Sun provides just the right amount of warmth to keep water liquid. Mars receives less, Venus more, but both are still within a zone where the Sun's energy has profound effects on climate and chemistry. Beyond that zone, sunlight is too weak to sustain life as we know it. In this sense, the Sun's influence fades not the heliopause or the Oort Cloud, but within a few AU, in a narrow band where its energy can support ecosystems. This is another boundary, one defined not by physics alone but by biology. When we ask when the Sun's influence fades, the truth is that there are many answers. If we mean light, the fade is gradual, becoming negligible beyond a few hundred AU. If we mean gravity, the fade is never complete, but the point of dominance ends a few light years away. If we mean the solar wind and magnetism, the fade occurs at the heliopause, around 120 AU. If we mean the ability to sustain life, the fade occurs much closer, within a few AU. The Sun influences space in overlapping ways, each with its own reach. There is no single line that marks its end. Instead, there are layers of fading, each relevant in a different context. This layered fading also shows why defining the solar system's boundary is so difficult. Different criteria give different answers. If you measure by planets, the end is Neptune. If you measure by icy bodies, the end is the Kuiper Belt or scattered disk. If you measure by the solar wind, the end is the heliopause. If you measure by gravity, the end is the Hill sphere, nearly 2 light years away. Each answer is valid depending on what kind of influence you care about. The Sun is like a ruler with many concentric zones, each one defined by a different kind of power. From a human perspective, the fade of influence is also psychological. Standing on Earth, the Sun is everything. It dominates the sky. It determines the seasons. It is central to our sense of time and place. But if you were aboard a spacecraft heading outward, you would watch the Sun diminish. It would become a smaller and smaller disk, then a point, then eventually one bright star among many. At that moment, the Sun's dominance would no longer be obvious. You would see the galaxy around you, and the Sun would seem like only one participant in a much larger system. The fade is not only physical, but perceptual. It is the change in how we experience our star as we move away. The Voyagers, now beyond the heliopause, are living examples of this fading. Their instruments record plasma and magnetic fields, showing that the Sun's wind no longer defines their environment, and yet they still orbit the Sun, however loosely. They still send back signals powered by radioisotope generators that keep them warm against the cold of interstellar space. They are no longer inside the sun's bubble, but they are not entirely free. They will carry the sun's gravitational mark with them for millions of years. The fading of influence also reminds us of scale. Light fades quickly with distance, dropping by the square of the distance. Gravity fades more slowly, but its dominance is eventually lost. Plasma and magnetism fade at hundreds of AU, habitability at just a few. The solar system is a set of nested boundaries, each with its own radius. To ask where the sun's influence fades is to ask which aspect of influence you care about. There is no single edge, no single answer. There are only zones, each marking a different kind of transition. When we imagine the solar system, we often think of it as a single entity. A star with planets, moons, asteroids and comets, all bound together in a shared cosmic family. But the truth is that the solar system does not exist in isolation. It is not a bubble floating in emptiness. It is part of a galaxy, orbiting among billions of other stars, drifting through regions of dust, gas, and magnetic fields. At some point, the influence of the sun gives way to the influence of the galaxy. That in-between zone, where one domain fades into the other, is the border between the solar system and the galaxy. It is not a wall or a sharp line. It is a gradual transition, complex and layered, where different forces trade dominance depending on how we measure them. We can start by considering the solar wind. This constant stream of charged particles flows outward from the sun, inflating the heliosphere. Inside this bubble, the solar wind dominates the plasma environment. Beyond it, the interstellar medium, the thin soup of atoms, ions and magnetic fields between the stars, takes over. The point where the two pressures balance is the heliopause, crossed by Voyager 1 in 2012 and Voyager 2 in 2018. At about 120 astronomical units from the Sun, the heliopause is the first real marker of a boundary between solar and galactic influence. Inside, the Sun sets the rules. Outside, the galaxy does, but even here the transition is fuzzy. The heliosphere expands and contracts with solar activity, and the interstellar medium itself is not uniform. The border shifts, flexes and ripples, responding both to the Sun's rhythms and to the larger galactic environment through which it moves. Beyond plasma, there is light. The Sun's illumination diminishes with distance, fading by the square of the distance. At the edge of the heliosphere, sunlight is still brighter than the galactic background. But by the time you reach the Oort Cloud, tens of thousands of astronomical units away, the Sun is no longer dominant. It shines only slightly brighter than neighbouring stars. Seen from there, the Sun would be reduced to a star among stars, still visible but not overwhelming. In terms of light, the border where solar and galactic domains blend lies somewhere in the outer Oort Cloud, where the Sun's glow becomes just another point in the sky. Gravity extends farther still. The Sun's pull never fully ends because gravity reaches infinitely, but it weakens with distance, and eventually other forces matter more. Astronomers describe the region where the Sun's gravity dominates over galactic tides as the Sun's Hill sphere. For our star, that sphere extends perhaps 2 or 3 light years. Inside it, objects can remain bound to the Sun, orbiting over timescales of millions of years. Beyond it, the pull of the galaxy is stronger, and objects drift away. The outer edge of the Oort Cloud is thought to lie near this boundary. By that measure, the solar system's border is not at Neptune, not at the heliopause, but nearly halfway to the nearest star. But even this gravitational boundary is not static. The Sun moves through the galaxy, orbiting the centre once every 230 million years. Along the way, it passes through spiral arms, interstellar clouds, and regions with different densities. Each environment changes the balance of forces. When the Sun passes through a dense interstellar cloud, the heliosphere may shrink, exposing the inner solar system to higher levels of cosmic rays. When a nearby star passes within a light year, it can disturb the Oort Cloud, sending cascades of comets inward. The border between solar and galactic influence is therefore not fixed. It changes over time, shaped by encounters and environments, by the galaxy's structure and the sun's journey through it. The border can also be described in terms of radiation. The sun produces a constant flow of energetic particles, but the galaxy is filled with cosmic rays, high-energy protons and nuclei accelerated by supernovae and other violent events. Inside the heliosphere, the solar wind deflects many of these cosmic rays, reducing their intensity. Beyond the heliopause, that shielding is gone and galactic cosmic rays dominate. For spacecraft and astronauts, this difference is important. Inside the solar system, radiation exposure is high but manageable. Beyond the heliosphere, it becomes harsher, a reminder that the galaxy itself is a more dangerous environment than the sun's bubble. In terms of radiation, the border lies at the heliopause, where cosmic rays surge. So where is the true border? The answer depends on what you measure. In plasma, it's the heliopause. In light, it's the Oort Cloud. In gravity, it's the Hill sphere. In radiation, it's the shielded versus unshielded zones. There is no single answer, because the solar system is not defined by one kind of influence. It is defined by many, overlapping, each fading at a different distance. The border between solar system and galaxy is not a line but a series of thresholds, each relevant in its own way. For humanity, this border is not just theoretical, it is the stage for our first steps into interstellar exploration. Voyager 1 and Voyager 2 are already beyond the heliopause, sending back data on the interstellar medium. They are still inside the Sun's Hill sphere, still orbiting the galaxy as part of the solar system, but they are tasting the environment beyond. Their instruments record plasma density, magnetic fields and cosmic rays, giving us our first direct sense of what lies outside the Sun's bubble. These measurements show that the galaxy is not empty, but alive with particles and fields, a place where the Sun's influence has ended and another begins. The concept of a border between solar and galactic space also changes how we think about our place in the universe. From Earth, it is easy to imagine that the Sun defines everything, but step far enough away and the Sun becomes one star among billions. Its bubble of influence is tiny compared to the scale of the galaxy. Even the vast Oort Cloud, stretching nearly 2 light-years, is small compared to the 100,000 light-year span of the Milky Way. The border between solar and galactic domains is therefore a humbling reminder of scale. The solar system is immense to us, but it is a speck within the galaxy, and yet the very existence of that border also makes the solar system feel more tangible. It shows that our star does carve out a domain, a region of space that belongs to it, shaped by its wind, light, and gravity. It shows that stars are not isolated points, but centres of influence, each with its own bubble, each carrying a retinue of planets and debris. The galaxy is not a uniform sea, but a collection of these overlapping domains, each star surrounded by its own version of a solar system. The borders between them are not always clear, but together they create the structure of the Milky Way. The Sun's border with the galaxy is therefore both a physical and a conceptual boundary. Physically, it is the place where forces shift, where solar plasma gives way to galactic plasma, where sunlight fades to starlight, where gravity yields to tides. Conceptually, it is the place where we stop thinking of ourselves as part of a single star system and start seeing ourselves as part of a galaxy. To cross it is not only to move from one domain to another, but to change perspective from local to cosmic. And so, when we speak of the border between solar system and galaxy, we're really speaking of a layered frontier, one that teaches us about the sun, about stars in general, and about the galaxy we all inhabit. It is not sharp or simple, but gradual and complex, reminding us that boundaries in space are rarely fixed lines. They are zones of transition, places where one influence fades and another rises, places that invite exploration and reflection. When we talk about the solar system, we often measure it in units that already stretch the imagination. An astronomical unit, the distance from Earth to the Sun, is nearly 150 million kilometres. That alone is almost beyond human comprehension, yet we use it as a convenient yardstick to describe the positions of planets, asteroids, and comets. Multiply that distance by 30 and you reach Neptune. Multiply it by 1,000 and you're still only scratching the inner edge of the Oort Cloud. These distances are vast, and yet they are only part of the story. To understand the solar system fully, we must also understand time, because the two are inseparable. Distance defines how far worlds are from the Sun. Time defines how long they take to circle it. Together they give us the scale of the system we inhabit. On Earth, we live by the rhythm of the Sun. One day is a rotation, 1 year an orbit. Our lives are structured around this cycle. It feels absolute, yet it is only local. Mercury orbits the Sun in just 88 days. Neptune takes 165 years. Pluto takes 248. Sedna takes more than 11,000. Each world experiences time differently, not in a subjective sense, but in the objective length of its orbit. If you lived on Sedna, a human lifetime would not even register as a sliver of one orbit. Civilizations would rise and fall, continents would shift, ice ages would come and go, all while Sedna had barely moved around the Sun. Time, when stretched across the solar system, is not uniform. It expands with distance, slowing orbits, lengthening cycles, making years into epochs. This perspective shifts our understanding of history. On Earth, the span of recorded history is about 5,000 years. That's less than half of Sedna's orbit. The entire sweep of agriculture, writing, cities, empires, science and technology has taken place during a single fraction of one orbit of a distant icy body. If we imagine Earth's history transposed onto Sedna's timeline, we realise how brief our presence is compared to cosmic cycles. Time at the edge of the solar system dwarfs human time. It reduces our sense of permanence, reminding us that even what feels ancient to us is fleeting on a cosmic scale. Voyager 1, now more than 45 years into its journey, has only just crossed into interstellar space. In human terms, that feels like an eternity. In cosmic terms, it is nothing. If Voyager were heading toward the nearest star, Proxima Centauri, it would take more than 70,000 years to get there. That span of time is longer than the history of modern humans. It is long enough that civilizations could rise and collapse many times before the spacecraft arrived. And yet, in galactic terms, 70,000 years is still short. Only a blink compared to the hundreds of millions of years it takes the Sun to orbit the center of the Milky Way. Distances and times are so large that our normal scales fail. Numbers become abstract, and only comparisons give them meaning. Another way to see this perspective is through the speed of light. Light travels at 300,000 kilometers per second, the fastest speed in the universe. Yet even light takes 8 minutes to reach Earth from the Sun, more than 4 hours to reach Neptune, more than a day to reach the outer edge of the heliosphere. To cross the distance of the Oort Cloud takes weeks. To cross to the nearest star takes years. The fact that even light struggles to keep pace with the solar system shows just how immense it is. For human-made spacecraft crawling along at tens of kilometers per second, these distances translate into journeys of millennia. Time and distance blur together, each magnifying the other. Think of comets. A comet from the Oort Cloud may take millions of years to complete a single orbit. For most of that time it drifts unseen in the cold. Then, briefly, it dives toward the Sun, glowing with a tail, visible from Earth for a few weeks or months. Then it retreats again into darkness, not to return for millions of years. For us, that visit feels like an event, something rare and dramatic. For the comet, it is only one moment in a cycle so long that we cannot track it within human lifetimes. The perspective of time and distance makes us realize how different the universe looks. when measured in cosmic terms rather than human ones. Even within the inner solar system, these scales matter. Earth and Mars are separated by tens of millions of kilometres, yet spacecraft take months to travel between them. Jupiter is so far away that signals take nearly an hour to make the round trip. Engineers planning robotic missions must account for these delays. Commands cannot be sent in real time. Each manoeuvre must be pre-programmed, each response delayed. The speed of light, instantaneous to us on Earth, becomes a constraint in the solar system. Time is stretched not only by orbital periods but by communication itself. Looking outward, the perspective becomes even more striking. The Milky Way galaxy is 100,000 light-years across. The Sun's orbit around its centre takes about 230 million years. That means the last time the Sun was in its current position in the galaxy, dinosaurs roamed Earth. In the time since then, continents have shifted, oceans have opened and closed, species have come and gone, and the solar system has travelled halfway around the galaxy. Our star and everything bound to it is in constant motion. The border between solar system and galaxy is not static. It shifts as the Sun moves, carrying its bubble of planets and comets through regions of higher and lower density, through spiral arms and inter-arm spaces, through changing cosmic weather. The timescales are so vast that even Earth's entire geological record is only a fraction of one galactic orbit. This perspective also changes how we view stability. To us, the solar system feels permanent. The Sun rises every day. The planets orbit predictably. But over billions of years, nothing is permanent. Orbits shift under gravitational interactions. The Sun itself evolves, slowly brightening as it ages. In 5 billion years, it will swell into a red giant, engulfing Mercury and Venus, perhaps even Earth. In 7 billion years, it will shrink into a white dwarf, leaving behind a planetary nebula. By then, the solar system as we know it will be gone, replaced by a smaller, colder system. These timescales are immense, but they are inevitable. The perspective of time shows us that even stars and solar systems are temporary. And yet, there is something grounding in this perspective. To realise that the solar system is vast, that its timescales stretch beyond imagination, does not diminish our place. It situates us. It reminds us that we are part of something larger, that our lives and histories unfold within cycles far greater than ourselves. The Sun may fade, the planets may change, but for now we are here, in the brief moment when Earth is habitable, when humanity exists, when we can look outward and measure these distances and times. We are participants in a vast story, and though our chapter is short, it is connected to the whole. The perspective of time and distance also inspires us to imagine. What would it be like to stand on a comet, watching centuries pass between each perihelion? What would it be like to live on a world so far away that a year lasted longer than all of recorded history? What would it be like to see the Sun as just another star in the sky, its warmth too faint to notice? These are not only scientific questions, but imaginative ones. They remind us that our perspective is not the only one. The universe offers countless vantage points, each with its own scale of time and distance, each with its own rhythm. In the end, time and distance are the keys to understanding the solar system's true size. They show us that the solar system is not just a set of planets orbiting a star, but a dynamic structure extending into the galaxy, bound by gravity, defined by cycles that stretch across millennia. They show us that human history is brief, that cosmic history is long, and that our moment is one point in a continuum that spans billions of years. You have travelled outward, step by step, from the warmth of the Sun to the farthest shadows where its influence fades. You followed the paths of planets, wandered with comets, paused at icy worlds, and drifted across unseen shells of debris and dust. Along the way, you've seen how the solar system is not a single edge, but a collection of boundaries, each measured differently, by light, by gravity, by plasma, by orbit. The truth is that there is no single place where the solar system ends. There are many edges layered like ripples spreading outward from a single stone dropped into water, each ripple fading gradually into the next. When you stand on Earth, the sun feels overwhelming. It is our star, our clock, our source of life. It gives rhythm to days and seasons, anchoring us to a sense of time that feels absolute. But as you step outward, its dominance begins to shrink. At Mars, its light is still powerful but weaker. At Jupiter, it is already distant, shining 25 times dimmer than at home. At Neptune, sunlight is a pale echo, nearly 1,000 times weaker. Beyond that, the sun fades until it becomes a small disk, then a bright point, then finally, in the far reaches of the Oort Cloud, just another star among billions. The change is gradual, but it is undeniable. What feels absolute at Earth becomes relative at the edge. The same is true of gravity. The sun holds the planets firmly, locking them into cycles that last for billions of years, but farther out its hold loosens. Objects in the scattered disk wobble under the combined influence of Neptune and the galaxy. Bodies in the Oort Cloud orbit so loosely that the passing of a single star can shift their paths. At the edges of the sun's hill sphere, the galaxy takes over. The border is not a line but a tug of war, a balance that tips depending on distance, mass and time. The solar wind tells a similar story. Close in, its stream of charged particles shapes everything from auroras to magnetic storms. But at the heliopause, more than 100 astronomical units away, it yields to the interstellar medium. Beyond that, the sun's breath is gone. The plasma environment belongs to the galaxy. The same applies to magnetism, radiation, and habitability. Each fades on its own scale, leaving behind a layered structure that is both beautiful and complex. As you picture these scales, you may realize how vast the solar system truly is. The planets, so familiar to us, occupy only a tiny inner ring. Beyond them lies a volume 1,000 times larger, filled with icy fragments, scattered bodies, and unseen reservoirs. The Oort Cloud stretches so far that its outer edge lies almost halfway to the nearest star. To measure the solar system this way is to realize that our star's domain is enormous, yet still a speck compared to the galaxy. The Milky Way contains hundreds of billions of stars, each with its own domain, each surrounded by its own spheres of influence. Together, these systems overlap, forming the galaxy's fabric. We are not alone in this pattern. Every star is both isolated and connected, each one holding tight to its own, each one contributing to the whole. And still, as immense as this is, it is not static. The Sun itself orbits the galactic center, taking 230 million years to complete a single circuit. Along the way, it passes through spiral arms, crosses regions of dust, and feels the pull of neighboring stars. Its borders shift and flex with every encounter, every environment. The solar system is not a fixed bubble, but a moving one, carried like a ship through the currents of the galaxy. Its edges are stirred, its reservoirs perturbed, its comets nudged inward, its particles stripped or replenished. Even the most distant objects are part of this dynamic journey, bound to a star that never stands still. For humanity, to trace these layers is to gain perspective. We see that what feels vast to us, the orbit of Neptune, the span of the Kuiper Belt, is only a small step in the hierarchy of distances. We see that what feels long in human terms, a century, a millennium, is brief compared to the cycles of distant worlds. We see that our presence, though fleeting, is part of a much longer story, one written in orbits and tides, in the interplay of gravity and time. The solar system is not just a backdrop for human life, but a framework that situates us within cosmic history. Voyager 1 and Voyager 2, our farthest travellers, have already crossed into interstellar space. They remind us that even with 1970s technology, we could touch the border. They still send back whispers, faint signals carrying measurements of plasma and cosmic rays. But they also carry the golden records engraved with human voices and music, a declaration that we were here, that we looked outward, that we cared enough to send a message into the infinite. Long after they fall silent, long after Earth itself has changed, they will continue to drift. Perhaps one day they will pass near another star. Perhaps they will remain lost in the dark. Either way, they are proof that the solar system's story is also humanity's story, that our curiosity extends beyond survival into meaning. As you think about the solar system fading into the galaxy, you may imagine yourself drifting with it. Picture the sun shrinking into the background. Picture the planets becoming invisible. Picture the comets suspended in the dark. Imagine floating in that vastness, weightless, timeless, surrounded by stars. There is no sharp edge, only a gradual blending. The solar system becomes the galaxy becomes the universe. You drift outward, and with each step, perspective expands. The familiar becomes small, then smaller still, until it is simply one part of something unimaginably vast. And yet, even in this infinite context, there is comfort. The sun is still our star. Earth is still our home. The solar system, however large or small it feels compared to the galaxy, is where we belong. To drift outward in imagination is not to lose that connection, but to strengthen it. Because in seeing the edges, in seeing how the solar system fades into the galaxy, we also see that we are participants in something greater. The borders are not ends. They are transitions, continuities, reminders that everything is connected. So here, at the imagined edge, let yourself rest. Let the distances stretch. Let the timescales expand. Let the boundaries fade. The solar system does not end sharply, and neither does your journey through it. It drifts outward, layer by layer, influence by influence, until there is no difference between here and there, sun and galaxy, solar system and universe. In that infinite drift, everything belongs, and everything continues. And so, you floated with me across the sun's vast domain, past the planets and their moons, beyond the icy belts and distant wanderers, into the shadows where the solar system dissolves into the galaxy itself. There's no hard ending out here, only layers that thin into one another, influences that fade but never quite vanish. The sun holds on close, the galaxy holds on farther away, and somewhere between the two is where we live our fleeting moment. As you settle now, let those distances and timescales soften in your thoughts. There's no need to measure them, no need to solve them, only to let them drift past like clouds carried by a quiet wind. The solar system continues outward, endlessly, and so can your imagination. If you found comfort in this journey, you can always join me again. A like, a subscribe, a quiet share with someone who might need a moment of calm. Each of those helps keep these explorations alive. But for now, there's nothing left you need to do. Close your eyes if they're not already closed. Let the rhythms of space carry you gently. Rest in the thought that even in this immense universe, you have a place. And tonight, that place is here, safe, quiet, drifting in the infinite.